All righty. Well, welcome everybody. My name is Jeremy Fischer. I'm here with a whole slew of people from a couple of different institutions to talk today about doing a deeper dive into containers and how it relates to scientific computing and gateway usage, and kind of give you an idea of where it's come from, where it's going, how you can use it, some best practices, a little of everything to talk about during the course of the day today. So it's going to be a rather long session, and we're going to talk about all the things we're going to do today. So here's kind of the outline. So you are here. We're in the introduction portion of the show. So I'm going to do a few minutes on the history of containers and a little bit about containers in general. Suresh is going to talk about the gateways tie-in. We're going to go into environment introductions, and then doing actual simple and complex builds, doing some exercises. We're going to have quite a bit on best practices and features. And then in the second part of the show, we'll start off with some Q&A back with me again, and then we'll have more exercises and best practices, and then a very specific section on containers for gateways, and then, of course, the closing questions and answers. So as we go, if you have questions, please do jump in or go to the chat. One of us will be watching the chat. If you would like to interrupt and ask a question as we go, that is absolutely fine too. We'd rather make sure all questions get answered than not. So without further ado, I'll go ahead and jump in. So again, I'm going to start the introduction about containers. A little bit about where we came from. So containers all have been around for a while in some form, and it all started from a very simple idea. The cheroot jail, so the change root jail, was a method that let users have a place to work without affecting the rest of the system. It was basically just a very, very simple modified environment. They couldn't access anything outside of that area, and became known as a change root jail or cheroot jail. This evolved over time into a bunch of different forms, and some different vendors had different takes on it. So you had Linux vServer and Solaris containers, and OpenVZ and Process containers by Google, but they basically all amounted to very similar things. What we saw change was LXC. It was basically the first Linux container system that didn't require kernel patches, and this was the original basis for Docker. So Docker really made containers popular. It was sort of a combination of the right tool at the right time, ease of use, and frankly, good marketing. The biggest potential downside of Docker was the need to run as root. And obviously HPC wasn't going to let you do that. Now, that's evolved a little bit over the years, and especially this year, we've seen some changes to that, and that's going to be discussed later on. But that was an early limitation. Then we saw some other container technologies evolve. You saw things like Shifter and Charlie Cloud and Singularity, and they gave different means of running containers on HPC systems. And today we're primarily going to look at Singularity as a means of using containers in HPC, but it's good to know about the others. And these were all born from the same general for the same general reason. That people needed to run containers in a secure manner where the user won't necessarily have privileged access, like if you were using your own laptop or using a cloud instance that you were running. So Charlie Cloud was developed at Los Alamos National Lab as a way to use containers in what you can imagine is a very strict security environment. Shifter was actually born from Docker code as a project between NERSC and Cray to scale up containers and HPC workloads. And many of the concepts that we're going to discuss today with Singularity may apply to those. The actual technologies are very similar, although how they do things is a little bit different. And then lastly, we started seeing people kind of up the ante into things like container orchestration. So different ways to run container workloads in a very broad and well-defined and well-organized way. So you started seeing things like Docker Swarm and Apache Mesos and Kubernetes. And it's basically all about managing the life cycle and workloads of the containers, being able to schedule and manage those easily, and to use true elastic computing techniques to grow and contract depending on your workload and configuration. Now, I will say we're not actually going to cover container orchestration as part of this tutorial, but if there is interest, we will possibly look at doing something like that in the future, though. Hello. There we go. So containers, and why would I want to use them? And it comes down to a few different things. So consistency, you basically want to have the same environment every single time you run, and you don't want to have to worry about the libraries on the host system. You don't have to worry about different compiler versions. Basically, you just want to make sure you have the same environment every single time. And that leads into portability. So you can take that environment anywhere you need to go from place to place. And again, you don't have to worry about setting up that environment in a new place. You don't have to worry about, you know, is this version of Ubuntu going to be compatible with what I'm using? You want to be able to package it and run on HPC. And again, you know, HPC environments are out of your control. Somebody else runs them. You won't be able to dictate what libraries and what things are available to you. So it gives you a way to package it up and kind of scale it up. Just-in-time instantiation. So basically fast boot. They're ready almost immediately. They're as easily dismissed, fairly easily updated, and very easily redeployed other places. It lets you create microservices. So it lets you have small, very purpose-built containers that have a single or at least an uncomplicated function. And these can be small and easily maintained and changed as needed without having to redo the entire stack. Running legacy code, and this is the one that I see most often, where people need to run on a very specific version of things because it hasn't been updated. And this lets people have that environment without having to worry about as much about security issues on the entire system. And lastly, reproducible science. So the name of the game is being able to reproduce your work and having others reproduce it as well. So containers do give you an easy way to at least keep one of the factors in this, your code and your operating system and all of the pieces that need to go into your analysis, consistent. And it's also just good to know. It's something I like to tell people when working with containers. It's always simple versus easy. The process is simple. It's not always easy. And hopefully today will shed some light on that and help you out with that. So I'd be a little remiss if we didn't talk a little bit about virtual machines. So several of us on this presentation also work with a particular cloud system that's National Science Foundation funded. So we run virtual machines as part of our process of daily life. But there's a very marked difference between containers and virtual machines and their scope, basically. So virtual machine is fully contained. Everything you need is there. All the parts of the operating system are there. So you have an independent kernel, you have independent libc, you have basically everything self-contained for an operating system. They're completely independent of the host. And basically they're considerably larger because of this. Containers, on the other hand, basically depend on the host for the kernel and for some other pieces of the operating system. And that lets them reduce their size quite a bit because they don't have to depend on all of the things to be an independent operating system. And the other part is that it's much easier to transport containers around for the most part than VMs. Virtual machines, within reason, you can pick up from one place and run in another, but depending on the vendor and depending on what it is, you might run into issues. Moving things out of commercial cloud is not always the easiest thing to do, whereas moving things from, say, an OpenStack cloud to another OpenStack cloud is fairly simple and typically is not difficult to do. That said, VMs are generally less transportable just because of the size, and again, because of some of the difficulties moving them around from place to place. So a little bit about Docker. I'm sure everybody has heard about Docker or used Docker. But Docker is a container technology. It basically, like I mentioned earlier, evolved from LXC, from Linux containers. They've since parted ways with that architecture, and they've created their own code base. It's very low overhead. Basically, the kernel usage is what makes it light, but it's also the potential danger area. You're not completely isolated from the host like you would be in a virtual machine. So there's another key difference there. It lets you have everything you need for your environment. So you can run it in any other Docker capable machine. And you'll notice the asterisk is there. Windows and Macintosh both have Docker releases. And you might be asking, well, how are you running Linux containers in Windows and Mac? That's because they have a small hypervisor that's actually included in the Docker distribution. So when you're running a Linux container on Windows or Mac, you're actually running a very small virtual machine running Linux. So it actually gives a nice way to be portable that way. Docker has a very, very well organized and large repository, and multiple repositories at that. So Docker Hub is the one most people know. Due to some usage issues with Docker Hub, we're starting to see other hubs pop up. We're starting to see more and more of those, and a lot of private repositories as well. But it gives you a nice place to be able to download, store, upload, share. Gives you a nice way to make a very robust environment for sharing your work and having containers for reproducible science. And because of that, it allows you to ship those out, which can be deployed pretty much anywhere. So kind of the big picture. So you have a client, which will be typically on your laptop or wherever you're working. That can be a virtual machine. It can be pretty much anywhere. You'll have the Docker host, and the Docker host can actually be the same machine you're working on, or it can be a remote machine. But you use your client to talk to the host that's running the Docker daemon, and that Docker daemon will talk to the registry to get images to pull down and to run or to update or whatever you're doing with them. But it's kind of the big picture that you have the client. It is a client server model. So you have the client typically where you are working, you have the host, and most people it's on the same host, but it can be remote, and the registry. So a little bit about how it's used. You can kind of see this is a little dive down into it just a hair. So you can see your local computer. You have your Docker instance running. So that's where the Docker daemon's running and the Docker client's running. So to the left, you have a Docker file, and that is a definition file. We'll talk about that a fair bit more shortly. But that is where you can have a sort of scripting for building a Docker image. You can use that Docker file to build your image. You can then run the image on your computer to have a running container. You can then do different things with that container. You can start, stop, restart. You can make changes to it, save those changes, push those changes back up to the registry. But again, this kind of shows you the life cycle of a container as used from your desktop. And to switch gears a little bit, we'll talk a little bit about Singularity. It's yet another container platform. So why are we talking about it? So it comes down to Docker was created with a single host and a single user in mind. It needs the host machine's kernel. It needs to run with escalated privileges. Again, that has changed a little bit, but typically where we've come from, it needs to run with escalated privileges. And so to scale workloads up, you needed to move to an HPC cluster. And to be frank, they're not going to give you root access. You can either find a way around that, or you can get used to running your workloads on a lab server or your laptop or wherever you can have more privileged access. But we saw a shift in managing containers for HPC. And one of those evolved into Singularity. So Singularity was created to run containerized applications in HPC environments. It's one of the most popular, if not the most popular method for containerized HPC workloads. This is the system you'll see on pretty much all of the Exceed resources. And that's the National Science Foundation virtual organization that we all work with in passing. All of the resources there use Singularity. So we see that in a lot of places. A key difference is it allows untrusted users to run untrusted containers on a system that you are not privileged on. Your container processes run as you never receive any escalated privileges. And this should keep container usage from being a security issue. Singularity complies with the Open Container Initiative, and this basically concentrates on the interoperability with Docker. So you can use pretty much any Docker container in Singularity. You can pull from Docker Hub, you can pull from other Docker compatible repositories. It gives you a nice way to be able to use Docker in a shared environment. So actually, this slide is, again, still wrong, which I noted last time and still didn't change it. But we're going to move into a talk about containers and gateways. Before we do that, are there any questions? Okay. Sure. All righty. So with that, I will turn it over to Suresh for a discussion of gateways, the gateway applications. Suresh?
Yeah, thank you, Jeremy. Yeah, just give me one quick second. Yeah, so I'm going to not use the slides here first, like, for this audience, and like, first describe and connect to the rest of the agenda here. So as Jeremy has described, like, what we've been like, talking, the containers could be looked in the context of general eScience applications in two ways. One is the scientific applications, like, which run on the big machines. And when it comes to gateways, like, gateways have this increasing challenge also to run. How do we run the gateway middleware as we adopt as the gateways, or in general, like, if we take a look at any eScience architectures or scientific workflow systems or portals in general, as we adopt, like, the modern architecture, like the microservices architecture, where services get broken down into multiple components. And as we see lots of container orchestration framework come help in run multiple instances of these application containers and how to orchestrate them. So the gateways come in hand. For gateways, the containers come in two different application areas. One, the underlying scientific applications which run on the computational infrastructure. Second, on the, like, how do we operate the science gateway or workflow or eScience middleware itself. So in today's sessions, like, towards the end of this tutorial, in the last module, we'll do a hands-on on using some of the same examples, which we will go through in the first part of the tutorial on how to containerize an application and how to execute it. We'll see how we will run that from a gateway interface. And but we do our group, like, we do extensively use containers to operate the middleware itself. And if I know, like, for this audience, that might be of interest. If you have any questions or if you have an interest about that, feel free to ask us during the breaks or, like, during the Q&A, and we'll be happy to show. We may not have a hands-on on that, but we'll be happy to walk through how we are using containers to operate the middleware. But, like, but for the stay focused with our tutorial script, we will, like, towards the end of this tutorial, we will learn how gateways can benefit by adopting containers in scientific application portability. I think I'll stop with that, and then we'll have a detailed hands-on about this as the last module. Thank you. Thank you.
Great. Thank you, Suresh. So next, before we start diving into sort of the guts of how containers work and talking about Docker and doing some of our hands-on exercises, we're going to take a quick interlude to make sure that everyone who wants to have access to the hands-on portion does have access. And I'm going to give a quick overview of the sort of underlying stack that we're all going to be working on today. So that being said, we're doing our introduction to the hands-on environment and making sure everyone has access. Please speak up in Zoom chat if you don't have login credentials at this point. We sent out a Google Doc for everyone to sign in on, but I'm not sure that the link made it all the way around to everyone here. So first of all, just a quick review. We're going to make sure you all have access to the environment, take a Docker file and build it into an actual image, which you can run. And we're going to talk a lot about the distinctions between various pieces of the container ecosystem that get referred to in confusing ways, like image, and do you have your actual Docker and definition files, and the phrase container, which people use in a lot of overloaded ways. So then after we have a Docker container, we're going to build that into a Singularity image that is more suitable for running on an HPC system. And then we're actually going to run a job on our sample system using that container, so that you see how it typically, how easily it typically integrates into that existing environment. The environment that you'll be working on will be it's in a virtual machine on the Jetstream cloud. So everyone will have login access as a user onto a head node that's running the usual Slurm scheduler. This is very similar to a lot of the other big machines that we work with in Exceed that are just your typical HPC systems. And atypically, you're going to have access to Docker and Singularity with root permissions to actually build containers. But other than that, this environment is very similar to what you would see as a user on one of these big systems. The other small wrinkle that is kind of interesting is that this virtual cluster is entirely automated and elastic. So these compute nodes that we'll be running on later don't actually exist until you submit jobs. And if you have questions about how that works, feel free to ask in chat. We can send you resources. The sort of main pieces, like I said, that we'll be using are Docker, Singularity, LMOD, and Slurm. And LMOD is the module system that we use for managing user software environments. So that will set a lot of shell variables for you behind the scenes that give you access to the set of binaries that you actually want to use. For containers, this is sort of less important because everything you need is going to be baked in, but it can still be helpful for making sure that you've loaded the right version of Singularity, for example, on the resource that you're using. SSH credentials will not be distributed via email. We are sending them out via chat. Please speak up. My other co-presenters are waiting right now to hand out passwords from our list. And this, again, is only if you want to participate in the hands-on portion. And again, this link needs to be updated to point to eScience 2021. I'll get the right link up in chat here. Container tutorial, eScience 2021, and we want our part 3. Oh no. There we go. Okay, so here's a link to the correct GitHub page. So all of our hands-on exercises are going to be, we have a written walkthrough in GitHub. So if you want to come back and look at this later, you're more than welcome to. And we have all of the steps that you'll be following are written in code blocks like this. We will be using Vim for any file editing, but you can use other Linux file editors of your choice. I believe Nano should be installed. Emacs may not be installed, sorry. Let me know if that's a problem and we can fix it. Any lines that start with a $sign like this indicates a command to actually run. And sometimes we'll have output in the code blocks that will show you what you should be seeing. So please feel free to speak up and let us know if you don't see something that we've indicated you expect. And when we are doing these, I will be following along on screen, or one of our other presenters will be doing this on screen so that you can see what it will look like as you go along. We also have conventions, 2 different conventions around variables. If you see something in angle brackets like this means that you need to replace this with your actual username. So like instead of I am username, this would say it should be replaced with train01 before you run that command. And occasionally we'll also have those variables in proper bash format with a $sign and curly braces, and that will just work if you copy and paste it. But it's, we have these 2 different conventions just so that you're aware. And once you have your username, you should be able to SSH onto our virtual machine at eScience-contoot.jetstream-cloud.org. I know that was a mouthful. I've got it highlighted here. And you should, either from Windows, Linux, or Mac from a terminal, you should be able to run this SSH command with your train number at host name and get access. So I'm gonna wait just a moment. I think I don't see anything on fire in my side Slack channel. So I'm going to go in as train 98. And make sure I get the last G in there. And I'm going to copy paste my password in. So, and you should see the same message that I'm seeing without the last login sign. So once you've logged in, all the files that we'll be using are stored in opt ohpc pub examples. This virtual cluster is built using the OpenHPC project as the underlying source of RPMs for most of the important software. And just to make sure, you're looking at the module system, you should be able to run these module avail commands to see the list of available modules on the system. So these are sets of software that are pre-installed and available for users. We don't have much because everything we need is going to be contained in Singularity or Docker. Typically, you'll have several different stocks of OpenMPI and scientific software available if you're not familiar with this kind of thing. One thing that's really nice to be able to see is if you do the module show command, you can actually see all of the things that are happening behind the scenes when you load a module. So if you, for some reason, need to find the actual path of something, you can typically find it in the module show information. Like if you're trying to compile something yourself and you need access to the location of a set of libraries or something, this comes in handy sometimes. So that being said, I'm going to pause and wait for questions if anyone doesn't have access, but otherwise, we'll move on with an introduction to Docker from my colleague Sanjana. So any questions, anyone not have access, feel free to unmute and interrupt. I think we have a small enough crowd that shouldn't be a problem. Okay, take it away, Sanjana. Thank you, everybody.
Checking if you guys can hear me.
Loud and clear.
Yep. Good morning, good afternoon. I'm Sanjana Sudarshan. I'm a senior technical advisor for Jetstream, work for Indiana University. And today I'm going to give you a brief introduction to simple container creation. So this is going to be a run through of some of the basics. You don't have to do any hands-on right now. We will work on some hands-on later, but I'm just going to give you a brief introduction to a Docker file and such. So I'm going to turn my camera off and dive into my slides. All right. So if you have Docker installed on your machine, one of the ways to check if Docker is installed is to just run the Docker command. And if you run Docker, it'll give you a bunch of lines, which gives you all the options you can run with the Docker command. You can also run a Docker -- version, which tells you what version of Docker is installed on your computer. Another way to check if Docker is installed and if it's running is to run something as simple as docker run hello world. And what this basically does is it runs the image hello world on your system. If it is unable to find it, if it's not locally present, it'll say I'm unable to find the image, and then it'll download the latest image and run the image. So these are just some ways to check if Docker is installed and if it's running properly. So Docker containers are created by objects in Docker called images. An image is as defined by Docker is a read-only template, which has instructions for creating the Docker container. These instructions define, I'm sorry?
Sanjana, I think we're seeing your notes. Do you want to have the slides full screen?
It is. There, can you see that?
I see nothing now.
Oh.
No,
Sorry about that.
Thanks, Peter.
I mean, you could still see the slides. Okay, I just figured you probably want a full screen.
Let's see.
It's usually me who does this, so.
There you go. Is that full screen now?
Yes, that's right.
Okay. So, right. So these instructions define everything the container needs. So what it needs to run, if it needs any specific software to run, any dependencies, code libraries, etc. So these instructions are packages within an executable package, which is the image itself. So when you run the executable package, you create a Docker container. So in this example on screen here, I run a Docker run alpine ls-l. So in this example, I'm running the Alpine Linux container, which is a lightweight distribution of Linux. Docker fetches, when I say Docker run alpine, it's not available locally. So it fetches the Alpine latest image from the Docker registry, saves it to your local system, and then runs a container. And once it runs a container, it'll then do a listing of all the files in that container. So some useful commands with Docker is running Docker images. So Docker images will tell you all the images that are available on your system. So in this case, I've run Alpine, Hello World. So I see these two images on my system. If I ran something like Docker run Alpine echo Hello World, then the output to screen would be Hello World. So what's happening here is Docker is running the Alpine container. And within that container, it is echoing hello world. So this is all I see on screen. Docker PS gives you the process status of your containers. So when I run Docker PS, I basically see nothing. And this is if I have no containers running at the moment. So if I want to see all the containers that I have run in the past on this system, then I can do a Docker PS -- all, which will tell me the container that I just ran. And that here I see that it was exited a few seconds ago when I took the screen grab. So Docker PS will list all running containers and containers that you have exited. All right, so we look at a few examples of deploying our own applications with Docker. So we will do some hands-on containerization later, but let's just take a look at this example now. So in this example, create an image that sandboxes a small Python application. And we do that by writing a simple Python script. And the script checks if the input number is odd or even. Then we Dockerize it by writing a Docker file, and finally build the running image. So we start by creating and cding into the simple script directory. Within that directory, we will create two files. First one is app.py, which is our Python script, which checks if a number you input is odd or even. The second is the Docker file. So let's talk a little bit about the Docker file itself. A Docker file is a text file that contains a list of commands that the Docker daemon calls while creating an image. A Docker file contains all of the information you need, that Docker needs to know to run the app. So a base Docker image to run from, the location of your project, and any dependencies it needs, and what commands it needs to run at startup. So this is a very simple way of automating the image creation process. All right, so walking through this Docker file, our base image is going to be Alpine version 3.9. So from Alpine 3.9, we run. So the run command will install Python pip package to the Alpine Linux distribution. And this will not only install the pip package, but all dependencies that includes the Python interpreter. The copy command will transfer or copy the file we created, which is our app.py, into our image. So the app.py is copied into our image at this location. And the last step is cmd. This is the command for running the application itself. So the primary purpose of the cmd command is to tell the container which command it should run by default when the container is started. All right, so we can build our image with a Docker build -t. And excuse me, and if you have a Docker Hub username, it goes here, and you build your simple
Are we supposed to type in all these right now? Or?
No. We're just running through these examples.
Okay.
We will go through some hands-on containerization after this. All right, so the Docker build command, it takes an optional tag and -t, and the location of the directory containing the Docker file. The dot indicates the current directory. So a Docker build command does all the heavy lifting of creating a Docker image from the Docker file. So when you run the Docker build command, you make sure you replace your Docker Hub username with your actual Docker Hub username. This should be the username you created while registering on Docker Hub. So if you haven't done that, you can create an account on Docker Hub anytime you want. So when Docker has successfully built your Docker file, you can test it by starting a new container from your new image. So for that, you will do a Docker run. And again, you're pointing it to your app, and the -i indicates it is interactive. So when you run your image, it says enter a number, you provide a number, and your script should tell you if it is odd or even. Again, you can try these scripts later. Our slides are going to be available for you to look at later. So if you want to try it, you can do that after the tutorial too. Another example is, the dice roll.py. So this is very similar to our previous example. You cd into, and you make a directory called dice script and cd into it. You create an app called dice roll.py. And so you have this, I have a Python script for that here, and a Docker file indicating what's my base image, what I want to install, what files I need to copy over into my image, and what command to run while starting my container. Another example is Jupyter Notebook. A lot of people in research use Jupyter Notebook. So you can, to figure out what base image to use for Jupyter, you can do a Docker search command. So if you do a Docker search Jupyter, it will list all the base images available on the Docker registry. So you can say from Jupyter minimal notebook, and then you can have your Python script. And this one basically just says hello and your name. And for Jupyter, we need to tell the port which needs to be exposed, because Jupyter runs on port 8888. We will expose that port in this Docker file. And then you run you do a Docker build command. So you can provide your optional tag, your username, and the path to your script and your current directory. Now, if I run Docker images, it will show all the images that are on my system. So I have my notebook, simple script, and to run Jupyter Notebook, I run Docker run, indicate what port that I need to expose, so 8888, and the script I want to run. And so it will print out all these lines to screen, and then I can access my Jupyter Notebook by copying and pasting one of these URLs to screen. So similarly, this is an example for any biologists in the crowd. You can create a Docker file for SAM tools, which is a suite of programs for interacting with high throughput sequencing data. You can provide your optional tag with the -t command. And sometimes you just, if you have to install a ton of stuff, you can, there are other ways to do this, but you can also put it in your Docker file. And so you have a massive, humongous Docker file. So you say from your base image would be Ubuntu, and you want to install a bunch of things. And then you can run your command. Here I have SAM tools, but if you have any other command you want to run to start SAM tools when your container starts, you can have that in here too. So that's all I have. Any questions? All right. All right, no questions, then I pass it on to Steve. Is it you next?
Yes, it is. Hello, everyone. So we're going to get started with a quick tutorial, which I'm going to send out the link here shortly. I hope everyone can see it. There it is. Or everyone can get to it. And I'll send it out in the Zoom chat.
If you think of questions too, feel free to drop them in the chat. Or if you guys need a break, say something. We can do interactive as we're going along.
And we have planned for a 30-minute break after this section, I believe.
Don't listen to what I say, listen to Eric.
And I'm going to share my screen so I can work along with you guys. So I'm Steve Bird, in case you hadn't noticed. I'm going to just walk through this. I work on the Jetstream team with some of the other colleagues here. Yeah, and I think everybody's cracking to get into it. So first off, can everybody log in? Has anybody had any problems logging in yet?
Oh, good.
Okay. So as long as you guys can see my screen, basically I just
Could you
logged
increase
in.
the font size?
Oh yeah, I always do that. That's probably also why I went the wrong way. How's that?
Yeah, that should do. Thank you.
Okay. So first off, I just logged in. I didn't do anything crazy yet. Everyone has the host name, right? And everyone can view the documentation page on GitHub that I sent out in chat. Okay. So first, we're going to use some example files that are found conveniently in opt ohpc /pub/examples. So we can copy those over. No, we don't want to copy those over. I'll show them to you right now. And in there, we can see we have 3 different files there. We're actually going to be copying over this GitHub repo. That's my mistake. The first thing we actually want to do is make a directory to hold all the stuff we're going to be doing today. So for this, let's name it ex1 workdir. And just like that, and we're going to keep everything in that directory so that we can keep everything contained throughout our exercises today. This one's ex1 because it's going to be the first exercise we're going to go through. And then once it's created, we can change directory into it. And now we're going to actually git clone the repo. Which was the opt ohpc /opt/ohpc/pub/examples, and then it's the Mandelbrot zoom -py. And once that's done, we can see we have another directory, the Mandel zoom py, which is actually what we copied over. And if we change directory over into the Mandel zoom, you can see we have 5 different files. We have the Docker file, which we can look at right now. And as Sanjana was talking about earlier, that's the file that actually creates the Docker container. And inside this, inside the Docker file here, we're using a slim Debian distribution base image for the base, and then after that, we're going to run a few simple commands. We're going to run apt update, which will update the repositories to list the latest versions of packages that are available. And then after that, we're going to install quite a few different things here. And these are all just dependencies for the actual commands that we're going to be running here later on in the actual container. And then also, like it's noted, there's some Python dependencies that are installed as well. This can be done using a requirements.txt file, but we're just doing it in the container. That's kind of the good thing about containers, or well, maybe the bad thing, depending on how you look at it. There's so many different ways to do the same thing, which makes it kind of difficult if you're using someone else's container, but at the same time, it's possibilities are endless. And then from there, we're going to be copying in some files, the parallel.mandel.py file, which I'll show you in a second, but that was copied over when we git cloned in the zoom mandel.py. And we're going to put those in the user local bin mandel, parallel.mandel.py. And those are just copying them into the container themselves, so we can run them while they're in the container. Next up, we're going to just do a quick permission modification to make the zoom_mandel.py application readable and executable by everybody, but only writable by the owner. And then finally, we're going to set the entry point to run the actual command. And we're going to also add the command --help when you run it. So if you don't pass any arguments into the container when you run it, it'll just show you the help, which is useful because you can see a list of everything that you need to do or everything that you can do with this specific container. And like I said, those two files that we're going to be copying in are also there as well, the parallel.mandel.py and the zoom_mandel.py. There's also a definitions file, which we'll talk about later. It's not going to be important for this specific example, but it will be later. And then there's also the README from the Git repo. Are there any questions so far? Okay. Next up, we can start using some Docker commands. The first one, Docker images. It just shows which images are currently built on this specific server. As you can see, we've got only two, an Alpine container and then a Hello World container. These are pretty simple containers. As we go through ours, they'll start to populate and we'll have a little more on there, which we can actually build right now. If we run Docker space build -t, put in and then if we put in our username, so for me, that's train20, and then you can give it a tag here, and then do not forget the trailing period. That's often overlooked. You'll error out. It's not a terrible error, but it is kind of confusing if you do forget it and don't see it.
And all that's doing is telling Docker to look in the current directory for the Docker file. Exactly,
as Eric pointed out. Okay, so we went through a few lines pretty quickly. That's at the beginning. So first, it's just pulling the slim Debian image and running it in an intermediate container. You can see, here that it discusses an intermediate container as it builds. So basically what's happening, that's okay, Eric. So basically what's happening as it builds is it's building a container, running that specific script. So for this line here, it's running the apt installs, and it's running that inside the container, the intermediate container. And then once it's done, it's saving it. And then as it goes to the next step, it'll create another intermediate container based on the previous. And as you can see, it does this about 9 times throughout the whole thing. So yeah, it's just pulled the image, ran the apt update, ran the apt install. It gave us a lot of stuff here. And this is all apt output. And it's pulling packages. Wow, it's pulled a lot more than I anticipated. If you forget the trailing period, I can actually show you here. It's not bad, but it will. It says an error about it couldn't find the Docker file or something along those lines. This is a lot of output. Come on, I'm going to show you. While that's running. Did everyone get it to run okay?
Okay, Steven, now it's very minute. This font size is very small now. You could resize it again.
What was that?
No, the font size of your terminal.
Oh yeah, it shrank again.
Yeah.
Sorry about that.
Thank you.
I'm not used to presenting the actual iTerm page. But if you forget the trailing period, yeah, this is it'll just okay, so that's what it spits out. Docker build requires exactly one argument. And yeah, since we don't have the trailing period, it doesn't have it can't find the Docker file. And then since the -t is just a flag argument, it doesn't know what to do. It's basically like running a command without passing the argument that's necessary. Ooh, this is still unpacking. Is everybody running their building their container right now? And it's going through the same thing?
Yes, it's doing the same.
Let's take a look. All right. I feel like it's installing a lot more than it should have.
Should we be able to read your text? It just seems really small to me.
Oh, I can. This is The short answer is yes. This isn't important. This isn't too important right now. But yeah, you should be able to. Is that one smaller than the other one? Yeah. Is that better?
I don't know if there's a delay. It looks either the same or smaller. Actually,
Yeah,
they both
both-
kind of. They
Both in
look
the
kinda small.
browser and the terminal are pretty small.
Is that?
Yeah, that's better for me.
Okay. So while we wait, we can take a look at see if there's any images that are built on here. Yeah. Okay. So since ours are building, it looks like there's mine and 2 others that are building. They're not done yet because they don't have a repo or tag.
That's a lot slower than it was last time I tried this out.
Yeah. I will say not having a repo or tag is probably not the best indicator that it's still building. But since we're building it on the other terminal session, we can assume that's what's happening.
So there was a message from tech support about a good way of reducing the number of install packages. I don't know whether you saw that in the chat.
I didn't see it. Yeah, that's a good point.
What's your base OS on this image?
It's Slim Debian. I can show you.
Okay.
Or Debian.
Yeah, so it's interesting. Sometimes you end up actually being better off if you pick a beefier base image just because it already has some of the things that you might need. It really depends on what you're trying to work with though. But I think last time you ran this, it was less. So
yeah, last time we ran it, should have ran it last night, or yesterday, but I didn't. I did not.
It may be that so we're using a date tagged version of the base Debian image, and I suspect that apt update may have pulled in a larger list of new packages than it. I know the update isn't pulling in packages, but since the image is a bit outdated now, it's probably pulling in more packages than it did when we originally wrote this.
this is a great moment to talk about reproducibility of your containers. Oh wait, we do that later.
Yeah, so the date for the Slim image is from June, so it's 3 months ago. So, but at least that step is done. Spooling up another container and running through the Python 3 scripts to install pip and upgrade pip and wheel, pillow and numpy. numpy. Or is it numpy? It's numpy. Anyways, so through our last steps, these all went a lot faster.
Are we debating the pronunciation? I think it's numpy.
Yeah, they're the chuckleheads are. Anyways, so copying the file, yeah, it's gonna be pretty quick, and changing the permissions, setting the entry point, also very quick. And then, so that's built. So we can check our images now. And it looks like everybody who was building theirs also built as well. The one thing I will note for train 01, I think, no, it's not a problem, but I did want to point it out. I think you tagged it with latest instead of oh no, it looks like somebody else is still building too. But it looks like you tagged it with latest instead of slash, which I think is Philip, right? Not that it matters. I did just want to point that out. Anyways, so it looks like everybody's done building. So we run Docker images. We can obviously see those on there. And then we can see which Docker containers are built on the system. And then if you run Docker PS, you can see which ones are actually running. And obviously we just built them, so they're not running. But that's actually our next step, is now that they're built, we can run them with Docker run, Docker space run space train 20. And then we can pass it the tag. And then this is where the command will come into place. So we're not actually telling the container itself what to do. It's going to run through the -- help command, which is right here. And we can look at the usage for the zoom mandel.py. So we have -h or -- help, which is this page right here. We can send it the number of nprocs or multi-processing threads, duration, the number of steps in the zoom, the starting frame, the size of the starting frame, the size of the ending frame, and the origin. So some of these, as you start ramping up, you can imagine it takes exponentially longer or more resources to complete the actual Mandelbrot zoom. But in our tutorial, I think we're going to give it a pretty quick one so that it runs pretty fast.
Yeah, this first run by default will just create a single image instead of an actual animated GIF. But we'll do bigger ones very shortly.
So I'm just going to copy this command and then go through it as I. So Docker run -u, we're passing it a user. So my ID -u, that's just going to print out our username. So in my case, it'll be train 20. For everyone else, it'll be their specific name as well as our group. And this is just so our output is for our user instead of root. As you can probably assume, if it's set to root, it's not going to be readable by us since we don't have root access. Excuse me. And then the -v of the path of working directory, we're just passing it our current path, so that way it'll bind mount our current directory. So the output will end up where we are presently. rm-true. rm-true, as you can read from the GitHub page, you just make sure the container is removed after the script finishes. This is generally a good idea if you're, well, it's a good idea in general, but it just helps ensure that you're a good custodian of your space and resources. If you leave them running, if you leave enough running, you can really tank the system or leave a lot of clutter. And then this is the actual command running. Well, this is our container here. It's going to, we want to pass our user, like in my case, it's train 20. And then we're running the Mandel zoom container. And then the last bit here, we're passing it the path of the working directory. And then we're outputting it to test.gif or GIF. And then I'm going to go ahead and punch that in. And check chat while it's running. That's gonna take some time. Definitely not as long as it took to build the container, but Isaac says, unable to find train 4. Isaac, I'm guessing you're train 03. There's a hyphen between.
Yeah, I found it. Sorry. Missed
Okay,
that.
okay.
Thanks again.
Oh, yeah, that's what Philip said. Okay. And Philip also helped with renaming. Okay. Thanks, Philip. Yeah, and so let's go back. It's still running. Oh, it's done now. I should have ran Docker PS to show. I guess I could run it again. Test2.gif. And then if we switch back over, we run Docker PS. We can see my container is running right now with the name of hopeful Rontgen. Don't know what that is. Anyways, but that just shows that the container itself is running. Is anybody else having any problems, or is this all working for everyone? Any questions even?
I'm just having difficulty getting the SCP to work.
Okay.
The file's there.
Yeah, SCP is going to be probably one of the harder points of this example.
Yeah, I know that will work on a Linux or Mac machine. I'm not 100% sure if if SCP is built into PowerShell now or not. I think it is.
No, I'm running it under a Mac, so it should work.
Okay.
I'll just pick up the full path rather than the relative path.
Do you mean WSL when you say PowerShell? Because
No, I
they're
don't.
not the same. Okay, good.
Yeah.
I'm just making sure.
Yeah,
Windows and WSL though.
Yeah, Windows recently added SSH support in PowerShell. So the normal terminal that you fire up.
Oh wow.
Yeah, that was a game changer for our last tutorial too. We didn't have to walk people through MobaX term or anything. Sorry, I'll stop on this sidebar.
Yeah, so as you can see, I have both those GIFs created, and now you can run SCP to bring them over to your local machine. I'm going to try this. I usually don't, but
No, it worked with the full path. It just doesn't like relative paths.
I think this one is the actual GIF itself is going to flash, just as a heads up. Now, let's see if I can run it. Oh, yeah, thank you. I always forget. Oops. I didn't want to do that. Not that web pages or that actual text is important. Because this one is just my computer. Yeah. Yeah, it should be, it'll be gray and black flashing.
Hopefully it won't flash anymore, actually.
Oh, really?
Should just be a single frame, yeah. Someone pointed out that that was a hazard for people that are photosensitive, which I should have caught sooner. Yeah, it should just be a single black and white image of the Mandelbrot set. We'll make some more interesting GIFs later on.
I can open it here. Oh, I said it's not displaying as a GIF. It's
Nope, no,
displaying as
it is still flashing. Great.
Luckily, mine doesn't open as animated already, so you can see the two pictures, the two frames of the Mandelbrot. Yeah. So that's the end of my first exercise. Is there any questions so far?
And share my screen. And as before, if anyone has questions, feel free to unmute and chime in. I don't think we're such a big crowd that will be a problem. And please let me know if you can't hear me or can't read my text on the screen. So, like I said, I'm going to talk about the Singularity container runtime environment, which is really what I mean when it's the thing around the actual container image that makes running it possible. So I'm going to talk about this mainly from a user perspective, not so much from an administrator perspective, though that will come up in the course of this. So Singularity was designed from the beginning to specifically work with HPC environments. So it's got tight integration with like your Slurm scheduler or Torque or PBS or whatever, with MPI and with module systems typically used. And that's done primarily by having a tight coupling between your local shell environment and the actual Singularity process. And in addition to that, it does not allow processes to run as root by default like Docker does. So it's now the case that Docker has rootless mode. That was not always the case. And so Singularity had a much quicker uptake in HPC environments because of that design decision. And the other sort of HPC friendly piece is that containers are generated as just a single file. So you don't have, there aren't layers that are cached in a database somewhere that you're pulling from. Every time you invoke a container, it's just reading from a file system. And under the hood, Docker is also just reading from a file system, but this image as a file format is a lot more friendly when a user needs to be highly aware of where they're reading from. Like in an HPC environment, when you can be reading from different network mounted file systems, or it can be important to have everything you're reading from in Scratch versus your home directory. So that makes things a little more, what's the word? I don't know, conceptually graspable for users who need to play nicely with their file systems and the sysadmins who are running their HPC systems. From the user side, there are a lot of environment variables set by modules that you're using, and those are transparently passed through to the running Singularity process. Root is required for building images, so you're not going to log into a cluster and start building something there in your home directory unless it's very explicitly been allowed by the administrators. And the last time we tried to do that, it was fairly non-trivial. So you're going to see a little bit of ugliness when we build our Singularity images on the test virtual cluster. There is every user of Singularity gets a .singularity folder in their or directory in their home directory, and that's where both where image caching happens. So when you pull a Singularity image, there's some metadata is stored in the .singularity directory, and there's also some configuration files that you can modify to control like what remote container repositories your Singularity commands will look to automatically. And a lot of this can also be changed by setting environment variables or putting them in config files in your .singularity environment, .singularity directory. It's not common to have to modify this, but it's helpful to know where that is in the case that you do. Like if you're working on a system where disk usage is important, you can change where your Singularity image cache is to be in a more system-friendly place,
or in
instead of in
case,
your home directory.
or in case where you have quotas on the home directory, maybe.
Mm-hmm. Exactly. So like I said, you can configure the remote repositories in a remotes.yaml file. There's also a subcommand of the Singularity command to add a new remote repository. So in the Docker environment, there's sort of the main Docker hub that is pointed to by default. Singularity typically uses cloud.scilabs.io, which I'll point out later, as the default image repository. And I think it's a lot more common with Singularity to have to configure the repository that you're pointing at. You can also, this is also where your PGP keys are stored if you're signing your containers, which I believe is an active feature in the community edition at this point. And like I said, this is where your cached images are stored, which you can change via the Singularity cache.dir environment variable. There's also, you can have a config.yaml file in your .singularity directory to change some of these things. And there are again commands to interact with your cache on the command line with Singularity cache list and clean. And if you actually go in and look at this, there are separate directories for containers that you've pulled on the system depending on their source. So if you look in library, you can actually see the Docker layers that are pulled down before they are converted into the Singularity CIF format. There are separate directories for OCI compliant images and a separate directory for image metadata. And it's important to be aware of this mainly so you know where you're taking up space on the file system by running some of these commands. Caching is also important because it keeps your containers up to date with the remote repository. So like if you have a build workflow where you're building from GitHub, pushing up to a repository, and then you just point to say the latest tag. This caching mechanism is how Singularity checks to see if your current image on the local system matches what's in the repository. So it's useful to be aware of this. It's actually preferred on a lot of HPC systems to just pull down a .cif file and use that local file in your Slurm scripts or PBS or Torque, so that your compute nodes aren't calling out to the repository and hitting those endpoints with every node in your job. So it's a lot of Singularity repositories are running on sort of smaller systems, and it can be easy to overwhelm them if you run a job on like 50 nodes and they all call out to that repository trying to download this image. I've heard stories about Singularity Hub administrators getting upset because they were being hit so hard by individual jobs. So it's a lot friendlier to use a local CIF file, but the cache mechanism is important to be aware of if you're pointing to a URL as part of your workflow. Singularity files are referred to as definition files. It's basically the same thing as a Docker file with a few extra pieces that make them a little bit user-friendlier in my opinion. There's no concept of layers, but you can have multi-stage builds in your definition file. And there are, instead of having individual commands on each line, they're based on sections. So each section can have a set of similar commands that are not prefixed with the actual command, like in a Docker file where everything starts with run or copy or whatever your command is. And you can have multiple copies of each section in a Singularity file, which is useful when you bundle in different applications into the same container, depending on your workflow. The top level section is called your header naturally, and that defines where you're getting your base container from, which depending on where you're pulling from, you have different options in this header section. Typically, you're just passing in the bootstrap, which is what Singularity calls the source of the container image. And then you're telling it where to actually pull that from, which is where you'll specify the actual sort of URI of the container. So that'll be the name and the tag. And Singularity does support pulling Docker, obviously Singularity and OCI compliant images from repositories like Harbor. And there are some OS specific Bootstrap agents where Singularity has built-in scripts available, like you can specify that you're using a CentOS Bootstrap agent, and there is a script predefined as part of Singularity where it will build sort of a clean CentOS image as the base. And I know there are Ubuntu images. There is an Ubuntu Bootstrap agent, probably Debian as well. If you prefer to build that way instead of pulling from a specific container image. So the Bootstrap agents are defined like Bootstrap, and then you pass the library in that you wish to use. This is what the sort of syntax looks like for, I'm sorry, let me rewind. This is what the Bootstrap agent for quote library looks like. And this means that you're pointing to a remote repository defined in your Singularity configuration that is a Singularity library of images. So by default, it points to cloud.scilabs.io. You can customize this, obviously. And the syntax for giving the container name looks like entity, collection, container name, and then the tag. So this is specific to Singularity registries. Entity by default is library, which is this cloud.scilabs, but if you've created your own repository or using a local one, you'll have to change this. If you're pulling from Docker Hub, it has a slightly different syntax. So you tell it you're bootstrapping via Docker, and then your from directive takes on a different syntax. So you'll give it a registry name, the namespace, which is in the Docker world, typically the user who's created that container, then the container name, :tag, and then you can pass in a specific hash with this @ symbol. And this triggers automatic conversion from a Docker image, which in the past was not always successful. I think now the automatic conversion is typically a lot smoother, and we're going to use that today in our example, though we are going to also walk through building our container with a Singularity specific definition file. So once you have the setup or the header section defined, there are sort of the build specific sections. The sort of highest level, most dangerous one is the setup section. It's not recommended to actually use this because you can take actions as root on the build host. So if you're on a shared system, it can be easy to break things. This is one of the things where you're required to have root access to run a definition file with this section in it. It's mainly there so you know what this is. If you come across it in a container that you're investigating, like I said, I don't recommend using it. you don't need it, there are other options. The next common thing is seeing the files section. So these are all defined with % and then the section name, and then typically you have a convention of an indented section with the actual commands specific to that section. So anything under setup just looks like a bash command. You can change the shell interpreter for this, but everything we do is going to be in bash. In the file section, you're just passing in the file source and the file destination inside the container. Unlike Docker, you don't have to have all of the files available in your current working directory, which is both good and bad. So if you pull down the source for a Docker file, it will have all the files you need in that repository typically that get moved into the container. If you have a Singularity definition file, you can point to things that are outside of your Git repository that may not be available on all build hosts. So that's one thing to be aware of that can break reproducibility of a build. So it's convenient, but also somewhat dangerous. In your post section, this is where most of the actual build will happen. So you'll run things like apt-get update, apt-install, make would happen in here typically, creating and changing directories or permissions of the actual applications you're installing. You can pass things from the post section into the environment at runtime by echoing directives into the Singularity environment variable. So anything in this will be put into the user environment when the container is actually run versus being built. If you need to grab some kind of information at build time and make it available to the user, and there's not another mechanism to do that. So like if you wanted to make the date available, you can pass the build date into the Singularity environment. So every time the container is run later on, the user has access to this now variable stating when the container was originally built, container image was originally built. Singularity also has a test section where you can set up a variety of tests for your container at build time. So you can validate things depending on the software that you're building. I think that pretty much speaks for itself. You can write tests in bash or source in a script to run and make sure the output looks like what you expect it to. And that's something that's not available in a Docker file. The environment section explicitly set variables that will be available at runtime. And these are things that you don't expect to change during build. So if you can basically manually set environment variables here. But if it's something that's generated during build, those environment variables need to be set during the post section. So this is sort of hard coding things like port numbers and things like that. The run script is similar to the CMD directive in Docker. This gives the default command that's run if you just do Singularity run container name. And if you're building an image to be run as a long-lasting service, there's something called start script that does the equivalent thing. So there's sort of a typical difference between that. Singularity is typically for a single run batch type job, and Docker is more appropriate for services, but both of them do actually support the other typical paradigm of running them. It's just not the typical use case for the communities that are using those container runtime environments. There's a help section where you can define things that your users will see when inspecting the container. It's very friendly to add documentation here and links to, say, the sources of your software and things like that. And it's available via the Singularity run help command, giving in your container name. And you also have the option of packaging multiple apps in separate sections by defining a new app in your definition file. And this would actually look like a whole new sort of set of sections that are specific to this app that you define. So you get separate post, environment, and run script sections, and then there's a Singularity run app and then container name. And that will invoke a different run script particular to the app that you've defined, which is useful if you have a multi-application workflow, but it's more convenient to package that into a single container. So you're not having to pull down lots of different images to support a single workflow. And the last thing is there's a label definition, a label section that allows you to define metadata about your container, like who made it, what version it is. And it's basically a key value pair delimited on the first space. So the types of images that you can build, there's sort of two main types, is that you can have a default immutable image so every time it's run, it pulls from that .sif file, and the user has the same environment every time. And that's the typical output of building a container is a Singularity image file format. You can also create sandbox images for testing. And that basically gives you a directory that is it's like a Purge environment where your container exists, that your container process is launched from. So you can create the sandbox environment, do your work to develop your container, build your applications, make sure it works, and then convert that directory into a SIF file for portability. It's a lot easier to transfer a single file than a whole directory, a whole file system, basically. But if you do need to have a writable sandbox image, you can build one and get into it via Singularity shell, which will launch a shell in that sandbox environment. And everything that you do will be written to local disk. Like I said, it's possible to run services using Singularity via instances, which is sort of the same nomenclature as a running VM in most cases. It's not real common because typically we're talking about HPC systems where you're not running services as a user, but could be valuable to know if you're very into the Singularity world and you need to use that for to support some kind of workflow where users may be coming in and submitting something to a service that calculates something for them. The other thing that is a typical problem to run into when you're running containers is mounting of local file systems into the container container process file system. By default, Singularity makes pretty much the whole file system available to the process, so it's very transparent to users. All of these mounts are done by default, which is a lot more than what Docker does. You remember when we ran our example, you actually had to bind mount your current working directory in so that you could get your output files out. And if you need to add something differently, like if your container application expects data to be in a particular location and it's actually somewhere else on the host file system, you can rename that with a bind directive at runtime. It's not often necessary because your container process is running as your current user. So anything that your user sees on the file system, your container process will also see. And the other piece that makes Singularity very HPC friendly is the tight integration with MPI. So the Singularity process picks up all of the environment variables that are set in your current session for MPI or that are set through currently loaded modules. So you can use the host MPI to run an application that's built with a compatible version of MPI inside the container for your jobs. So this lets users bring their own MPI applications to an HPC system that they have access to, which is good for both users and sysadmins. The only caveat is that you have to have version compatibility between the MPI used inside the container and the MPI versions installed on the host system.
Eric?
Yep.
Can I throw in a tidbit?
Absolutely.
Sorry to totally interrupt. Actually, I'll turn on my video. There is another consideration that I felt like we should throw out there. So if you are using MPI and you want to use containers multi-node on HPC systems, you must consider whether the underlying hardware will require special drivers. So for example, TAC, the Texas Advanced Computing Center, has a certain environment set up for some of their supercomputers. For example, Stampede 2 has an Intel OmniPath interconnect, and you will actually be required to install certain drivers so that the multi-node communication will work at all, let alone be performant. And so sometimes you have to start with base images that have these drivers. So just a caveat there that if you're working on an HPC system and they have specialized hardware, it's not a function of the containers or the MPI, it's a function of the specialized hardware. And so it's one way in which HPC containers become less portable. But that is a specialized hardware problem, which I just wanted to add that caveat because it has bit me.
Yeah, that's a good call. I was gonna touch on that, but I think you gave a clearer description of it, having been the one to actually be bitten by it. Thanks.
Sorry for jumping in. I meant to mention that before.
No, that's good. We should add that to this section. That's a very important thing to be aware of. I also add that I do not love building systems with OmniPath. Let's see. So the other option is that you can, instead of just building software in your container that's compatible with the host MPI, you can, if you have root access, you can actually bind mount the local MPI libraries into the container at build time. Let's see. Yeah, at build time and runtime, so that you're relying entirely on the host version of MPI, and you don't have a separate version installed in the container at all. But that requires access to a build host with the same versions of MPI and the same locations of everything as the system on which you'll be running, which is significantly more difficult to set up. So if there are questions, I'll take those now, but otherwise, we're going to move on to more hands-on fun with our virtual cluster and making Singularity versions of our Mandelbrot application. So any questions, just feel free to unmute or send something in chat, and hopefully one of my friends will let me know
I have
that
a
there's
question.
a chat. Yeah.
How does the mapping work of user and group IDs from within a container that's writing into a location that has been bind mounted from the host? Because with Docker rootless, that's a huge pain. And so I was hoping that they maybe have found a better solution here, because basically the way I understood it in Docker rootless, the only real way of doing it is that you run as root within the container, and that maps to the whatever user you are on the host.
Mm-hmm.
And those are the exact permissions that you have in the mapped in the bind mounts, which is annoying if, for example, there's a file where on the host you are in the group that has read or write access to that file, but in the container you aren't, and then there's no way of accessing that file.
Yeah, that's a problem. I haven't played with Docker rootless mode much yet, but if I understand correctly, the difference that should be much easier in Singularity, because the container process itself is started as your user on that system. So everything, the highest level permissions are the permissions that you currently have as a user. And that should see the same sort of group and user permissions that you would expect to see in a normal shell session. And it's actually etc password from the host is by default mounted into the container space. So it should be completely transparent with Singularity.
Yeah, that's what I thought because it maps the password file.
Yeah.
That sounds good. Yeah.
Yeah, it's a nice change from having to deal with Docker mounts.
Yeah.
and permissions, because I've run into a few of those struggles before on smaller systems.
The direct access to the file system that Singularity has solves a ton of these kind of small, like file permission issues and things like that, that you don't, the design was so that you wouldn't even run into that,
Yeah.
which I think is a nice feature for HPC. And Docker has a lot of sort of extra steps to make it HPC friendly, in my personal opinion.
Yeah, sounds promising.
Any other questions before we get hands-on again? I'll take that silence as a no, but again, feel free to pipe up. So going back to our GitHub repository, in part B, where you were running Docker before, there's a link to part C. It would probably be good if one of my co-presenters would paste that into chat for me. And in this section, we're actually going to take our Mandelbrot Zoom file, convert it to Singularity, Mandelbrot Zoom container, convert it to Singularity, and then run a job with it on one of our worker nodes to make a bigger, nicer GIF file that isn't as flashy and horrible. So again, I'm going to run alongside in my train account. And please let me know if my text is too small or anything. I'm using this horizontal split so you can see the full width of my shell. So we're going to take our Docker file, our Docker container, and make it usable in our hybrid HPC environment. I sort of mentioned earlier that our build host is also the head node for a cluster. So we're using Slurm. Hopefully we'll have all of the commands built in here as well, if anyone's unfamiliar with Slurm. First thing we're going to do, though, is make sure that we have our Singularity module loaded. So that you actually have access to your container runtime environment. And we're using version 3.7. Always important to know what version you're using, because there are cases when Singularity went from 3 to 3.4, I think it broke reverse compatibility with some older versions. There's definitely no compatibility between images built with Singularity 2 and Singularity 3. So something to be very aware of if you're running on a new system. Let's see. So I'm back here in the work directory, Mandel Zoom Pi, and I'm going to walk through. We have a definition file provided, so you don't have to do lots of typing or copying and pasting. And this is actually going to pull from, this definition file pulls from Docker Hub, and it pulls down the same Debian Buster Slim image that we used before. So this is sort of a direct translation of our previous Docker file into Singularity for comparison. We're actually not going to use this. We're gonna display conversion from the image that we already built. So we're not gonna have to sit through the whole process of updating all the libraries in this image. So the first thing we're doing here is just taking our files directive and copying our Python application, which comes in 2 pieces, into user local bin mandel in the container file system, just like we did before. We're updating our OS dependencies using apt. So the post section will look very different depending on what your base OS is. We're updating our Python dependencies very explicitly here. Again, you typically would use the requirements.txt, but it's a little bit more clear what's happening since we're doing this as a learning example. And we're making sure that our script is executable. Just changing the permissions on it. And then we're setting this as the run script. I'm not adding the help flag here by default. That's actually what it does. And I have a brief help explaining what we're doing. This whole thing is actually also available on GitHub. And I think we have a link to that on our sign up sheet. So that's all that happens here. Again, direct translation of the Docker file. I really like that you don't have to prefix everything with run, and you don't have to have lots of and backslash to do multiple commands at the same time like you do in a Docker file. But instead of going through and building that by scratch or from scratch, we can sort of take advantage of the work that we've already done. So we can pull directly from the local Docker daemon that's running on our system. Typically, this looks a little bit different from pulling from Docker Hub because there's this other syntax used to communicate with the Docker daemon that's running locally. And that looks like this. This used to look more like let me slow down. If you were pulling from Docker Hub, you wouldn't have this -daemon part, and it would be more like Singularity pull :/ like a typical URI, and it would point to Docker Hub by default. So it looked like this. Say if I had put this on Docker Hub, you would run something like this, and it looks like a standard URI. But for talking to a local Docker daemon, the format is slightly different. So this is a useful tool. It's kind of an unusual case. But you tell Singularity to pull locally, you give it the name of the output file first, and then the location of the container that you want to convert. Very nice. So I actually didn't run the first part of this on my user. So I'm going to pull from Steve's image, which will be the exact same thing. And this will take a minute to pull. It will pull down all of these layers and convert them all into a single file. So you'll see a lot of output here where it's copying each layer of the Docker container, turning it into a blob, and then packing it into a Singularity image format file. And this goes pretty quick because it's all pulling from the local daemon. So this is really just moving pieces on the local file system to a different place on the local file system. I think one of the reasons that I talk so much about knowing where your container layers are being stored is because in the process of developing these tutorials, I've broken quite a few VMs by filling up the root disk before we got the proper volume mounting set up to handle all of the extra files that are generated. So once that's done, you should see a mandel.sif or whatever you decided to name it. And one of the nice things you can do is actually, there's a few commands here to inspect the metadata of the container that you just built. Since we built it ourselves, there's really no surprises here. But if you're pulling something down or someone's already put a useful image on the system you're working with, These are very useful to see where it came from. You can see sort of general metadata about it that's automatically generated. And then you can actually inspect the definition file that was used to build that container. So if we had built this using our definition file, you would see that whole definition file here in the output, which I think is incredibly useful for scientific workflows where sharing the provenance of your applications can be important. That's one of the things I really don't like about Docker is it's hard to see how a container was built. So was everyone able to run these? Did it work for you? Anyone have questions about this part? No, pretty straightforward.
So typically when we use this, we run the Docker images directly under Singularity. And that seems to work quite well without doing the conversion.
So in that case, the conversion is actually happening at runtime.
Okay.
So all of this image unpacking still happens, and I suspect what's happening is that there's a cached version of a CIF file in your .singularity directory, and it will compare all the various blobs from the image you reference, and then compare that against your cache, and then use the CIF format that's locally stored. But yeah, you don't explicitly have to do this. You can just point at a link to a Docker container and let Singularity handle it. It's really gotten a lot smoother in more recent versions of Singularity. That's nice to hear that it works seamlessly for you.
Yeah, and some quite complex HPC codes, which amazes me.
Yeah. So for our next step, we're going to actually just walk through running a job with this container. I'm not sure everyone's level of comfort with using HPC systems. I suspect they're fairly high. Sometimes we run this for people that are sort of completely new to using these systems. So I apologize if this is sort of old hat. So we've provided a job file for running this container. It's in our examples directory in opto HPC pub examples mandelzoom.job. We were real creative with the naming. That's my fault. I'm a physicist. I apologize. Where I went to school, we actually had a building that was named the Huge Classroom Building in grad school, and it ruined my ability to come up with creative names for things forever. I was like, yeah, if that's okay, I'll just give everything the same name. So I'm just going to open this up. You shouldn't have to edit this file. If you want to, feel free. The main thing here, we're just going to run on a single node. I haven't written this to be MPI compatible yet. We're only using four cores. So if you make a really big zoom, it will take a while. But feel free to play around. This system will be up for a week, and you'll have access that whole time. So the run command is just your Singularity run path to the container image file, and then these are all flags to the application in Python, and we're going to make a much smoother GIF than before. I apologize for the flashing again. So we're telling it we're going to use 4 cores. We're going to have 50 milliseconds between each frame. We're going to have 20 frames. We're going to start with a window size of 2 in complex space, and the size of our final zoomed in frame will be 0.05 in complex space. I spent far too long looking at the Mandelbrot setting.
Yeah, where do you expect the job file to be? Looks like
So it's in slash.
I mean,
op.
looking at the, no, I mean, inside the job file, you have mentioned relative paths. So where should the job file be for all that to work?
I'm sorry, you cut out partway through. So that.
Sorry, can you open the job file again?
Yeah.
So here, all of these paths are relative, right? So where do you expect the actual file to be?
So you mean for like the Singularity image file? Or the
No, I mean this current, yeah.
I see, your job file. Yeah. So in our example, I have the job file put in your ex1-workdir so that those relative paths will hold true. In my case, I actually did not make the ex1-workdir, so I've sort of confused things, and everything is in my home directory. But I'm treating that like my work directory. So what I should do so in my home directory, I see this. Now I'm in my ex1 work directory. You should see your job file and your local Git repository of the application. Sorry about that.
Yeah, no problem. Thanks.
Yeah, you're welcome. Yeah, it's dangerous to use relative file paths in these things. The other thing, let's see, I'm going to go ahead and submit this, and then I'll talk a little bit more about what we're doing, because I think this takes a little bit to run through. Yeah, I see some of y'all are already running these. Excellent. The configuring state here is sort of atypical to see. This is because we're on a cloud system, so the compute nodes don't actually exist until you submit the job, and then Slurm runs a script to bring those up on demand. If you're already familiar with these, R indicates that a job is running. PD means that job is waiting for resources to be available. Since there's not 50 of us right now, we're not going to have that problem. Completed means that CD, represents a completed job, and F means that for some reason the job script exited with an error code. So back to our job file real quick. One of the first things I always do is module purge so that I know exactly what modules are loaded in my job, because your local environment variables will be passed on to your Slurm jobs. So you can get conflicts between the modules that you have loaded and the modules that you actually have for your application. Since we're using a container, you don't have to load very many modules. You really just need to make sure that honestly, I don't think we need to load the base compilers here even. Just make sure that you're pointing to the right version of Singularity on the host system. It's pretty typical to have more than one installed for compatibility with different images. So I always start out with module purge and make sure I'm loading the right versions of things. There's only one version on this system, so there's no need to specify a version number. Really, that's the last piece here. I already talked through what our arguments are doing. This typically runs for 5 or 10 minutes, I believe. When this is done, you'll get a better zoom.gif, which looks a lot friendlier than the 2-frame flashing thing. I've got a couple of interesting bits to zoom in on. If you spend some time reading about the Mandelbrot set, you can find some other fun points to make for nice zoom ins. Does anyone have questions? We've hit the end of this bit of hands-on sessions. I know Pete has some interesting demos lined up for you later, and we're open for questions. And after this, Pete's going to talk more about sort of best practices in building containers and making sure that they're reproducible and easily convertible between different systems. And like I said, feel free to play with the cluster, run more jobs, play with your parameters if you're interested.
I guess, I mean, one thing that I put in the chat earlier is there's a number of different container technologies, and one that's used quite a lot in Europe, particularly with the European Open Science Cloud, is UDocker, which is basically a user space Docker. Under testing, we find it has less overheads than Singularity or Docker. It's a bit harder to construct the images than Singularity, but the effort is probably worthwhile.
Yeah, especially if you need closer to bare metal performance. That's good to know about. It's just called UDocker.
Yeah, I'll find the link and put it in the chat.
Do you know what the main difference in the runtime is?
What do you mean?
So I guess I think I've heard of it before, but I haven't used it myself. So Docker and Singularity have kind of distinct differences in their runtime. Do you know what sort of the main feature differences between UDocker and Docker are?
I don't, sadly, I'm a manager. And so I rely on the clever people beneath me to tell me what's good and what's not. But I don't get into the details.
This is interesting. So I'm looking at I'll take over a screen share again real quick. I've got the documentation pulled up, and that was the very first question that they addressed, at least on their PyPy page. This is neat. So it looks like it actually extracts the container into something like a chroot environment. And it actually uses Singularity under the hood to start the processes.
Okay.
So I suspect it's extracting it and then maybe running it like a sandbox image.
Okay. I will probably say this again in just a minute, but Singularity does actually rebuild the container, the Docker layers into a new container. So that makes sense. They would use that as underneath. So you say that that's more popular in Europe?
It's certainly more popular for HTC, but it is getting leverage in the HPC community as well.
Okay, that's good to know. I apologize that most of my focus has been on American HPC.
No, I'm not unhappy with that, because internally we still run mostly Singularity for the HPC and UDocker for the HTC.
Okay.
Interesting.
Yeah, that is good to know. We have there's definitely some HTC use cases I could look at that for.
So Pete, I think you're up next if you want to go ahead and take over, unless there are more questions.
Yeah, another one is en route, which I used to use during my time at NVIDIA. We were using it on the DGX nodes. So we specifically build it for Selene. So that's again a low overhead container runtime. En route NVIDIA. I'll just post it on the chat.
Interesting. Thank you.
This doesn't have the root issues again.
Mm-hmm.
So yeah.
So this is another thing that's similar to, it sort of creates a chroot-like environment. Cool.
We deployed it in a few places in India actually. A few HPC centers.
Cool.
Traction there. Yeah.
Has much friendlier GPU support, I expect.
Yes.
don't
It
know.
majorly pulls from NGC, if you know about it. That's NVIDIA's container repository for GPU containers.
Okay. I don't know if this has been said yet, but there's kind of two other main container runtimes that we have considered, Charlie Cloud and Shifter as well. And depending on, so if you're using a NERSC system, you're using Shifter and things like that. But we've been asked this before, so I'll say it now. One of the reasons that we don't tend to cover those is they're different runtimes, in some ways similar to Singularity, some ways different, some ways similar to Docker, etc. And we have found that Singularity seems to be the one that a lot of folks have gravitated towards in Exceed, and all the tier 1 Exceed systems are using Singularity, and we're all in Exceed, so that's our excuse. But once you know, as we've kind of pointed out, once you know Docker and Singularity, it's a really good starting point to be able to move to the other runtimes.
Yeah.
So
we also investigated exactly the same ones. We found, I mean, this was maybe 3 or 4 years ago, but Shifter was actually much closer to a virtual machine. The size of the images was huge, and everything, literally everything, was embedded in the image. It may have changed since then. I can't remember why we didn't go with Charlie Cloud now. I know it had a bigger performance overhead than Singularity or Docker, at least for the use cases we were testing it on.
So I'm actually particularly curious about these kinds of conversations because I've recently joined a working group with some folks from various container runtimes and various computing centers that focus on the OCI spec for containers in HPC, and how the container runtimes, if you're unfamiliar with the OCI spec, I can send a link, but in the chat, but basically kind of standardizing container runtime environments to some extent, and addressing some of the HPC oriented concerns that often get overlooked for container runtimes. And obviously there are some container runtimes that have developed specifically for HPC, which we've been discussing a lot, but also sort of bringing that logic back to the OCI spec, and making sure all container runtimes are sort of making an attempt at least at some better support for these things. So yeah, definitely going to bring back UDocker as an interesting use case as well. Or sorry, HTC and UDocker and root to that conversation.
As part of this work group, are you actually looking at better accelerator support as well?
So we've just gotten started and we have an interestingly long list. One of the things we're really interested in doing actually is getting a better understanding of the sort of, this is off topic, I apologize, I'll try to be brief, but just the larger than just America. So we have some folks who are in Europe as well. I don't think we have much broader than America and Europe. We'd like to do that as well. So if you have anyone that you think would like to join this group, it's an open group, anyone can join. So I can put my contact information in the chat actually too, for anyone who's curious. But one of the main things we're trying to do right now is kind of get together a list of things that could be improved. And one of those tasks is a wider understanding of what the community needs are. And so we're putting together a survey that we're hoping to get out. That's my email. If anyone is curious about that group more, I can talk about that more later.
Cool.
So I'm up now, Eric, right?
Yes, you are up. You have 30 minutes.
Okay.
I'll give you a heads up in chat when you're getting close to time, don't worry.
That'd be helpful. And then we have, sorry, just to review the schedule. So then we have a break. And then do I have another section after that? I'm sorry, trying to get myself organized.
Jeremy is doing a quick Q&A and catch up after that break, which has typically been our lunch break. And then I believe Steve is going to do a quick MATLAB demo. And then you have containers for scientific research, including WRF development and other examples.
Oh, okay. Okay. All right. Okay. That's good. Okay, then I had something else in my head, so I had that wrong. Thanks for clarifying. Okay, so I think we'll jump right into, so I have some slides on, let me first get this full screen and then I'll share. Does anybody else have any questions while I'm just pulling this up? Okay. So I'm really happy with interactivity. If anybody wants to interrupt me and ask a question or throw it in the chat, I might not look that closely at the chat, so someone will have to potentially have to poke me to say something. But yeah, feel free to speak up or put questions in the chat at any point. Raise your hand, whatever you feel comfortable with, and I'll try to stop and make sure I address anything that comes up. But yeah, feel free to be as interactive as you feel comfortable with. And I'm gonna pause my Slack notifications, otherwise I will get distracted. Perfect. Okay, sharing my screen. Can everyone see my slides?
Yes.
Okay, thumbs up is also cool too, if that's easier. All right, so I'm gonna quickly go through just the process of converting from Docker to Singularity. And as I, let me see, sorry. As I go through this, feel free to, stop me or ask specific questions, but I'm going to try and go through these quickly and spend a little bit more time on my other slides that I have on some more advanced topics. And if I forget anything that I said I was going to cover in this time period, please feel free to remind me as well. So Docker and Singularity started from sort of two different philosophies. We talked a little bit about this, but I'll cover it just a little bit more. But you have Docker originally was really developed for more cloud type applications. And Singularity is more HPC. Docker daemon runs as root, Singularity runs in user space. And you have just completely different data management structures, file system access, and this interoperability that exists between Docker and Singularity is actually from the Singularity side. So Singularity was designed as a container runtime that would work for HPC applications, and Docker could work in Singularity. And so they are the ones who sort of, the Singularity folks are the ones who maintain interoperability between the two. And so because they have these different philosophies, there's kind of a different mindset about how to build containers for these runtimes. I think we've covered a little bit about that. But essentially, if you are deciding to build a Docker container or use a Docker container for an HPC application in Singularity, you probably want to design it slightly differently or make sure that it fits certain, kind of checks certain boxes to be able to convert it from Docker to Singularity. And so this is kind of the basic process. Is you start with a Docker file, and there are best practices for Docker files. And there are different best practices for Docker files that are going to become Singularity containers. And so that's worth noting. And there's documentation. I think they're in my slides. The links for both of those are in my slides. And if not, I will drop them in chat and make sure they end up in our repository somewhere. But this idea of creating a Docker file, you should follow the Singularity best practices, or if you're looking at something that someone else has created, if you can find the Docker file, ideally, you can take a look at whether those best practices are followed. and test, make sure that the Docker container works for what you want to use it for, tag that Docker container, push it to a Docker trusted registry, create the Singularity definition file or pull, as Eric, I think, demonstrated, and build and test the Singularity container itself, make sure that it still functions for what you want it to do. And optionally, you can push it to a Singularity registry as well. Oh, I already, oh no, sorry. So the best place to start is going back to the Docker file. If you're using a public image, again, look for that. If you have, we've mentioned Docker Hub. Docker Hub is sort of the go-to place for looking at images. And maybe later when I'm looking at our WRF images, I can show you a little bit about, if you're digging through trying to see what's inside a Docker image, you can also go there. And you can typically find a Docker file on GitHub for anything that has a public image. There's a lot of nice hooks between Docker Hub and GitHub. So people often will put these together. But without the Docker file, you don't know what's inside the Docker container unless you pull it and use it yourself. So it's good to sort of have the Docker file if you can. And there's actually have the linked version here is 3.5. I should probably update that, but Singularity is at 3.7 on some kind of main HPC systems. Some have gotten up to, I guess 3.8 is out now, I think. But anyway, so the best practices for Docker images, you can go to these Singularity docs, and they'll walk you through it. So I'm just gonna run through these. That's what these are based on. And on the right-hand side, you'll see kind of an example of what I'm talking about. As if this is on the right-hand side, that's like either Docker or Singularity file. So essentially, because Singularity uses the Docker root user as the user for the machine that the Singularity container will be run on, you don't want to make another user. Docker best practices usually recommend creating a user. Singularity best practices say just use the root user because we want to stick with just a single user of the system. And that user, the root user of the Docker container, becomes your user on the target system for a Singularity container image. So just sticking to the root user is the best way to go, and doesn't necessarily break anything if you make a user, but better to avoid it. And then, sorry. The best thing to do is, my phone is going on. The best thing to do is actually pay attention to changes that are happening in the underlying Docker image. And there's a couple ways I mentioned to do this. You can do a diff before you pull the image, and there's a container diff link there. But just kind of being aware that the Docker image changes can affect your Singularity container changes. And that's actually because Singularity does a rebuild of the Docker layers. And so you're getting a new image, even if you're pulling an existing image in Docker Hub, you're getting effectively a new container image in Singularity every time. So it is not one-to-one, but it is as one-to-one as one can get with a container runtime change, I believe. And if someone has some technical reason that it's not, please let me know, because as far as I've seen, it's pretty seamless, the one-to-one comparison, even though there are some differences in how the runtimes behave. So it's best to declare environment variables in the Docker file with the env command. You can also do a run, export or whatever, depending on what shell you're using. You can declare using run, but it's recommended that you use the env command. It's also recommended to avoid installing things to the /root directory. Sometimes you can get away with this, but user access, it's important to remember that Singularity gives you the access to the file system that your user has. So if you don't have access to /root on the system, you're not going to have access to it in the container. And it's important to keep that in mind. And it will be important as well if that particular path is expected to be read-only on the file system, maybe read-only in the container. it's generally just best to avoid installing to root. That's the simple way to say it. And we'll talk about other places you can install. Again, prepare for / in general to be the highest level, to be read-only. There are things like overlay file systems that can allow changes. Some HPC systems don't allow changes to the file system. There's a link there for persistent overlays if you're looking for something more dynamic. I'll get into why that is, the mindset behind that. And some of the best places to install is /opt or user local. Generally, if I'm installing a large set of packages in a container, I'll usually go for opt, and I'll set up sort of my own subdirectory in opt, and that's where all of my main packages go. I've also done user local, and it works well. Avoid placing things, again, just in the home or the temp directories, because these can get overwritten. And just a good sort of backup check is running ld config to make sure that libraries are linked appropriately when they get converted. Do not use plain text passwords. This is a security thing. And the run script environment is a good place to have your, rather than doing so I think in like the simple container slides, Sanjana gives an example of like using the cmd command. If you're going to have your container run something and you ultimately want to run in Singularity, it's much better to just put it in a run script within a definition file, or have a script that you can call from the command line that exists within your container. It removes ambiguity. So just a quick list of do's, because some of that's a lot of don'ts. Run the commands entirely as root in your Docker file. Do a diff on the base image before building a new image of your container, and use the end directive for environment variables, install to opt or user local, and run ld config at the end of your Docker file. And in general, protect secure information. This is across the board for all container runtimes and general computing good practices. So it's not a lot of extra steps. And generally for me, when I'm building a Docker container, if I'm not sure whether I'll use it in Singularity, I just follow these practices, and perhaps I'll set up a user. If you follow these practices for your Docker files, with maybe a couple extra steps for following good Docker best practices, they won't harm you, other than, like I said, potentially using the root user versus a regular user that Docker recommends. But you could certainly follow these practices and then add in Docker best practices if you decide to stick with Docker. I give an example of a completed conversion, and just simply, so you could follow through with this. I actually talked more about this in my other slides as well. But yeah, just this is an actual container for an astronomy use case, and essentially tag the container and go to the Singularity definition file here. You can use it, build the Singularity container, push the registry, again, the process. So other things to keep in mind, like I mentioned earlier, all tier 1 Exceed systems have Singularity. You can see the versions here. If you happen to have access to Exceed systems, it sounds like Singularity has much broader use just in Exceed 2 as well. If you have trouble troubleshooting a conversion, there are some really good tips. In my personal experience, it almost always just works, even for Docker files that do not follow best practices. So everything I just said, you can hypothetically ignore if it just converts. Basically, if you run into issues is where following these best practices helps you. And I have tended to find that the container itself just seems to run smoother if I follow the best practices. And I don't have the headache of having to worry about whether or not it will work. But I personally tend to build my own containers. If you're working with other folks' containers and it's a lot more hassle and you don't want to have to rebuild, troubleshooting can be a good place to go to fix just the things that are needed. If you're running on a non-Linux system, there's a tool called Docker to Singularity, a community tool that could be very helpful to you. All of these slides are in the GitHub repository. Actually, I think, no, No, I think they're in there. And so if you, or they will be certainly by the end of today. So if you have any questions now, it would be a good time. Let's see. Okay. Does anyone have any questions on Docker to Singularity conversion? If not, I will jump right into my other slides. I was just catching up on the chat. Okay. So Sean seems to have left us, so someone else will have to be our vocal vocal participant. Please feel free to speak up or say something in chat if you do have questions. Okay, jumping right into best practices and advanced topics. I should share my screen again. Okay.
Hey Pete.
Yeah, I'll just. Yes.
Can I jump in real quick with a timing
Absolutely.
question? So originally we budgeted for about 30 minutes for this section of yours. Is this a 10-minute section, or is this something that we actually would move into the next piece to go next to the WARF and development workflow?
So
stuff?
I will, yeah, I can go about 10 minutes and then just tell me when we're at time, and I can continue more later. But I'll probably try and get through a good portion of these now, and then have some more flexibility for if other folks have more questions later. That would be a good time.
Okay, that sounds good. I'll give you a heads up in 5 minutes. And quick apology, everyone. We are not going to talk about MATLAB today. We do have an example file in our repo, but we sort of removed that from our tutorial because it actually wasn't that interesting of a container. And Pete has a much more interesting example for you coming up. So I'm done. Pete, please continue. Sorry for the interruption.
Oh, no worries. I definitely interrupted you. I have a more painfully interesting container. Not pain for you, pain for me. Okay, so just a kind of a quick overview of what this section is about, and I will see how far I get through it. But essentially, I want to talk to you about the life cycle of a container. From the perspective of development versus production, how to, if you're considering sizes for different reasons, where your data goes, what you do with it, and then also just the various places you can put containers and use containers and how that affects how you design them. Security, I'll touch on briefly in this section, and some next steps that you can get into, which we'll probably talk more about later today as well. So everyone's probably heard of production versus development. I think this is an interesting topic worth bringing up here because it's a little bit different for containers. Oops, I already bumped myself ahead. Well, that's okay. Containers tend to be used for two different purposes. A production container isn't necessarily the same that you would think of as production software. It doesn't mean it's not necessarily iterated on, but typically containers start as development containers. They have GUIs sometimes. They often have editors of some form, extra things like man pages or extra sort of nice features for the human user and make it easier for teams to work together. They can be a lot larger. They have compilers and libraries that may not even be needed, but then production containers tend to have a more consistent, streamlined approach. You tend to only make the bare minimum of what's needed for the software to run. And these are kind of a great way to release software in industry, whereas development containers are often much more frequently used in research environments, and also sort of on the in industry on the development side of software development releases. And so I think I actually covered some of this real quick, but essentially in a production container, you want the code to be static, you want the image to be static, and then you iterate by tagging the container in a trusted registry. Whereas with development, it can be the container itself is often in flux, code is changing. People may even be running different versions of the same container and making changes within the container. The size could be enormous or small, depends on what you're doing, can have data visualization tools, whereas production tends to be much more lightweight, easier for the computer to run it rather than the human. And some people even store data within development containers. Production tends to be much lighter with run scripts to automate. And before I actually delve into container sizes, I actually just want to say container sizes matter depending on your use case. So I've often had folks say, why do you talk about container sizes? Personal experience with deploying Kubernetes in the cloud. It's actually my main reason that I think about container sizes. So the size of your container image directly impacts how quickly your cluster will spin up, which directly impacts the money that you are spending in the cloud. If you are running on an HPC system, the main downside is if you have an enormous container, you have to wait for it to upload. This can be annoying if, for example, on a system where you have to be in a interactive environment or submit a job to pull a container. And there are HPC systems like that. So that can be kind of annoying if you have a huge container and you have to wait an hour for it to download. So reducing the container sizes can be really helpful. If you're developing, it's typically not a big concern, but once you're running at in production at scale, and I'm thinking, 4+ nodes on a supercomputer, you probably want to have reduced the size of your image. So these are actually some old numbers I should probably update, but this idea of starting with a base image that's an operating system, you have a very pared down image. You saw an example of Alpine, you actually saw a Debian Slim image, which is smaller than this earlier today. So these are sort of just kind of some rough numbers, if you will. They're actually older, I should update them. But each command that you execute in a Docker file creates a new layer in the Docker container. And so combining commands is a great way to slim down your container, and other commands create temporary layers, but they end up ultimately being removed. Another method is, actually I talk about that later. So a really great example is if you're using Python, a pip command, a single pip command to install all of your requirements and using just a requirement.txt. So this actually is the same example container for the astronomy use case that I talked about earlier. And so here's one atrocious looking command, but it's actually quite good. It does a whole lot all in one step. When you're actually developing containers, sometimes you can break these up and make sure that things work, especially if something's failing, and then combine it later. So it's not the most important thing to do first, but it can be great for later. So again, still sort of a development. Yes, right. Multi-stage builds are another way to do that. They take advantage of the, excuse me, Docker build cache to reduce the size of your container, but they also can be a great tool for removing secure content. So if you need to use, for example, an SSH key within your container during build time, there are use cases I can think of for this, that we've done this. And then you have to remove the SSH key. A multi-stage build can enable you to use that secret information and then remove it as part of the build process. If you're looking at your doc file and you see several run commands in a row, that's an obvious example of something you could combine. I tend to combine logical processes in the sense that I'm installing a software package and all the files that need to be copied with it and all these different steps that need to be, the configure, compile, unpack the tar archive, I combine all that into a single run command, as you saw. And in general, the quickest way to get a smaller container is don't install what you don't need. If you have a development container you're happy with, just make a different container for production. And there are a lot of actually interesting ways you can go with HPC. A lot of people have developed, so TensorFlow, for example, automatically creates Docker files and then generates sort of pared down versions. A lot of companies are doing that. You can do something similar. You don't necessarily have to automate your whole process, but if you want just the binaries in a container for production to make it much smaller, that can be a lot faster, as opposed to particularly with HPC, with compilers, it can be a lot bigger, which we'll see in a bit. And you can also do the multiple containers decoupled, often called microservices, which is a different approach. That can cause you to have smaller containers move around more easily and be more flexible to compute in the cloud. So if someone else has built your image, you can decide whether or not to build your own. I definitely lean towards building your own. I think it's the best way to have security and control over what's inside your container and feel confident that you know what you're running. And also you can then share a new container with the world on GitHub, or you can look at other people's build files on GitHub as examples and just kind of taking a look at what other people have done in their GitHub repositories can help you to reveal unnecessary additions they have made to their containers that you can remove to have a pared down container if you're interested. And talking briefly about data management, which we've mentioned before, there's this sort of different philosophy between Docker and Singularity as far as how you interact with the file system. And here's just a VM as a comparison example. This is a common image for container runtimes that's reused everywhere. So you see that the container daemon or the Docker daemon actually is what does all the connection between the file system, the kernel, everything is through the container daemon for Docker. And so that's why you have to set up things like bind mounts and things like that to get actually access to the data on the host system. Whereas with Singularity, there's an added connection here. Singularity has a launcher that definitely interacts with the Singularity container and does a lot of the management, but there's a inherent connection to the root file system. And so you don't have to do any extra steps to have that access unless you want to make changes to certain types of access. So there are some good examples here of how to manage data. And so in general, access to the root file system is covered here in the Singularity user guide, but it's pretty straightforward. You can just try accessing a file and usually it'll just work. And if you need to do sort of some extra stuff, they're here. But the Docker methods tend to be volumes, bind mounts, tempfs mounts, and you can look more into that depending on your particular use case. And and so uploading containers to public registries is a good way to share. It's good for scientific research. This helps people repeat and reproduce what you've done. And it can also help build a community around a particular type of software or a workflow and help you to set up automated builds by connecting your GitHub account or particularly possibly some other source control methods and set up CI/CD, various things like that. One of the most common places to host, or the most common place to host Docker images is obviously Docker Hub. You get a unlimited number of free public repositories. And there's I think every user gets a single, this might still be their policy, I haven't done it in a while, but a single private a single private repository. And you can also set up organizations on Docker Hub. So we have an Exceed organization. I also have Cornell has I didn't even say who I am. I just realized that. I'm Peter Vaillancourt. I work at Cornell. I'm sure I was introduced earlier, but but I also work at the Center for Advanced Computing at Cornell, and we have our own Docker Hub organization on there as well, which is where one of my containers I'll show later is hosted. For Singularity, Scilab's cloud hosting is an option. It's got an 11 gigabyte limit for a user and to post public containers. And that sounds potentially like a lot or not a lot, depending on your particular use case. So I have containers that not even the container will fit within that limit. So definitely depends on what you're working with, what software and what the use cases are. So it could be good for you if you are using a lot of small containers, or you just want to host a single one. And if you're uploading to a public registry, don't upload private data, obviously, or licensed software. It can be a good idea to keep licenses with the software. It's not necessary to run, but even in a production container, it's good to have the license there. Protects you and protects, the software. Good practices. If you want to include in a public container, if you want to include documentation, that can be an option. Man pages as well. If you expect people to use your container as a development container for their software, you can create something more comfortable to use, and always make sure that your container has the dependencies that other people need to reuse your container. I have definitely experienced trying to use someone else's container where they had the dependencies installed outside of the container. They were able to make the connections, and the software worked for them and only them. So definitely try and include your dependencies. It's very good and helpful. And if you're doing production runs, it's always nice if you include an example script of how to run your container. And am I on time? There actually is already a question.
No.
So Philip actually says he's trying to run a Singularity container MPI. Eric did say you need to load the OpenMPI 4 module. Are you running this on our test cluster?
Yes, and I actually just did what I remembered from the slides. I'm actually not sure which model I'm using. I think it's the hybrid model.
Okay.
Yeah, but I was confused because I'm used to using srun to launch MPI jobs, but I guess that's a Slurm configuration thing. Also, the error I'm getting, I mean, if you don't run a job with MPI run, at least, I mean, what will happen usually is that you have a bunch of disjoint ranks, right? All report to be rank 0 and world size 1, but that's not happening in this case. So I'm confused as to what actually is happening that produces this error, which I've never seen before.
So Singularity actually recommends that you run MPI exec on the Singularity command itself, or MPI run. So whichever, am I covering my mouth? Sorry, sometimes I cover my mic by accident, just where my hand falls. So if I'm not audible, just tell me. So if you run, looking at your command, I don't actually see an MPI command outside. So you might need to do that as well.
Yes, and I just tried that, and actually that was the solution. Yes. So again, I'm on our cluster, at least I'm used to using srun in place of MPI run, but I guess that's not the case here. Yeah. Okay. So that works.
So was it both the module and MPI run, or did you try with the module and srun? I'm just curious. I might have the Slurm here configured differently than you're used to.
I did both, but I will try with just like the module and srun, and I'll get back to you.
Okay, thank you.
Thank you.
Since Eric won't do it, I will shamelessly plug Eric's self-scaling virtual cluster that he is using. There's actually a paper. He's written multiple papers about it. One of them he deigned to write with me, and I will reference that in one of my slides later. But so yeah, this is actually a cluster, virtual cluster it's hosted in Jetstream, right? This one?
Yeah, it's on Jetstream.
Yeah.
It's on Jetstream.
So you are running in an HPC-like environment in the cloud.
Thank you.
right, any other questions? Don't be shy.
Has anyone else tried to run an MPI job? MPI is fun. It looks like there are basically 3 people left who are not us. Is it lunchtime somewhere else that we should wait longer, or?
Yeah, I think there's a workshop and like 4 other tutorials that started at 4, like an hour ago. So probably we're competing for participants here.
I think we still do want to carry on for the sake of the recording.
All right.
Oh, right, yes. Well, I mean, if that's the case, though, that it's just kind of the 3. With less people, I would say, please feel free to unmute more often and just ask your questions that way.
Yeah, so I just got the result back, and it actually needs MPI run, so srun doesn't work.
Okay, yeah, so it's a slim configuration on my end then.
I guess, yeah.
I'll have to look at that.
All right, well, if there are no other questions, then I'll turn it over for the next set of exercises. I don't know which one of you that is, though.
That's me. So.
Oh, that's you. Okay.
This section is the Pete show.
Yay!
Although, if anyone else has ideas, feel free to jump in. I'm just gonna go through. So for this part, I'm gonna go through basically kind of covering a bunch of different container examples. I will finish my slides on the deploying containers in various environments. And I'm sad inside that so many folks have left, because this is where we actually do start to get into the deeper dive of the actual HPC. And then we're going to hear more about gateways. And so I think this is the exciting part. But I'll cover a little bit more about places to deploy, cover one particular example, HPC example in my slides, and then I'll dig deeper into a weather modeling example more recently developed, and I guess kind of leave it open for questions, some cool things I want to cover. And so anything I don't cover, I'm going to make sure there are links in the repository that I've already set up a further references markdown document in the GitHub repository. I'll probably add to it based on what folks say here, but there are some things in there. And I also have to touch on performance at some point, so I have to remember that. If any of that doesn't sound interesting to you, say so now, and I'll consider skipping it. Or forever hold your peace. Okay, so first things first, I'll hop back into my slides. So for this, yeah, please just, if you have any questions, please just jump in. Okay, so one of the major projects that I have been working on at the Center for Advanced Computing is something called the Aristotle Federated Cloud. It's 3 universities with federated clouds working together, essentially. And so a bunch of different science use cases have all been deployed on the clouds. And for every single science use case, we have containerized it. In the past year, we have particularly been focusing on comparing container runtimes, Docker, Singularity, and a Cornell developed container runtime called X containers, which you will probably not be interested in unless you are running in one of the public clouds, because that is a technology more designed to take advantage of spot instances. And so, and still in earlier development. So yeah, again, we're gonna focus here on Docker and Singularity, but in the cloud, there are a lot of options, and this is my only slide on it. So I have a lot more I could say about it. So if folks are interested in cloud deployments, please do say something. I think also Eric and Suresh can talk more about cloud to some extent with the gateways and how that overlaps as well. So any kind of questions you have in that direction, please do vocalize or put in the chat if we don't cover it. So essentially, a lot of what I have done in the cloud is HPC in the cloud. So if you're working with typical kind of containers in the cloud, that's a whole there's a lot more tools and industry oriented things that can help you out there. But for HPC, it's kind of a developing space, even within the developing space of the public cloud. And there's also private research clouds as well, which is part of what Aristotle is. And Jetstream is a public cloud, public NSF cloud. And so, yeah, so it's public research cloud, I should say, sorry. So when you're thinking about a container that you want to deploy in the cloud, you first have to ask yourself, is it going to work? Because HPC has more complexity. So you're really dealing with compilers, dependencies, MPI, and then also on top, and that's just for the container itself. And then if you want to deploy at scale, you have to consider orchestration. And so if you're thinking about single node, you can actually get quite a large number of cores on a single node in the cloud, depending on your available funds and other constraints, and where you're, are you memory bound or IO bound, CPU bound, those kinds of things. So all of those considerations come into a large space that I won't go too deeply into. But if you are curious about kind of getting started in that space, there's a paper talking about some of these. I think we used 3 science examples in that particular paper, and we have some forthcoming work about the weather modeling application that I'll talk about as well in the cloud. But that's one possible thing to look at, and there's a lot more repositories I can point you to as well if that's your space and you're curious. But essentially, Docker is what's often used in the public cloud. You can use other container runtimes, but there are so many managed services and container orchestration options. It's very easy to use. There's so many tools for it. Most folks just use Docker, even for HPC applications. Even with the added complexities that Docker isn't necessarily always set up for HPC, it still ends up being pretty easy in the long run to set up. I see chat. Oh, yes. So the, I'm not certain about the recording. Maybe Eric can answer that. All the slides will be in our GitHub repository and all the references. I'm going to go through some links that will not be probably, like I'm not going to give full explanations in the repository. We do continue this tutorial and it kind of evolves over time. So we will also be presenting at SC21 if you're attending there. I know some folks at this conference will be as well. And we're going to do a more formal in-person exercises at that, assuming SC21 is in person, then that's safe. Otherwise, we will continue with the virtual format, but I'm definitely planning to add some more materials to our repository. We also continually update the repository as we do new sessions, so we try to keep it always available. So I hope that helps, and you can always reach out to us if you have more specific questions. Okay. Oh, sorry, Philip then answered the recording question, so that's taken care of. Okay, so yeah, that would be. Oh, I forgot I have another cloud, yes, I added some slides on this, that's right. Okay, so the other question I was mentioning is, what is the right cloud? So the big problem with HPC containers in the cloud is vendor lock-in. So creating a container for an HPC application in and of itself is an undertaking, and then deploying it in the cloud is another kind of undertaking. And so a lot of private clouds use OpenStack, which has various options for containers. Public clouds have different options, and there are just so many options. And if you're interested in working on multiple clouds, let's say you get some free research credits on more than one cloud, which can happen, then you would really probably prefer to not be locked into a particular vendor tool. So that's another option to consider, and that can affect how you design your container, particularly if you're doing multi-node or MPI, things like that. And security is also a consideration when you're deploying in the cloud. It's really important, I think, to focus on VM level security first. Oops, sorry, I thought that would give me more bullets. Anyway, sorry. So the VM level security is really where you want to focus first. And so if you're working in the public cloud, there are some security concerns that they take care of, but a lot of it is actually on you. And it's very important, I think, to make sure you set up a firewall if needed, security groups, or whatever is the right method for that particular cloud. But just becoming aware of how to set up a secure VM in the cloud is something that is another task that you have to take on when you take on public cloud for HPC. And security is definitely something you have to focus on. Docker has recently released rootless mode as supported. That can be one particular advantage for more security systems, but also the vulnerability scanning is another option as well. And so, yeah, I would say keep paying attention to Docker's security options. When you're deploying on an HPC resource, I think we've talked a lot about this already, so I'll just kind of briefly overview. There isn't as much need to install things to your home directory, especially if they have the module system where you can just load a Singularity module and you don't have to then pester sysadmins to install the version of the software that you would prefer. I have heard of HPC systems where they actually install containers for you. You have to get the containers approved. And so that kind of takes away this benefit of the sysadmin not having to be pestered. But if the container is running in such a way that you can deploy your own containers, then that is a huge benefit of running on HPC resources with containers. And Singularity is available on XC. We talked about it's secure, the easy mounts, Slurm orchestration, and there are several batch systems that, I shouldn't say several, there are at least a couple batch systems that work with Singularity very well. And again, that's just a nice feature of HPC. It feels almost like you're not even in a container when you're working with Singularity. And you set up your job scripts, and something to keep in mind is that they may look different on different systems. So if you're working with, obviously if you're working with a different scheduler, it's going to look different, but even paying attention to the version of Singularity that's available, or whatever container runtime is available on your HPC resource, may change the job scripts, how MPI works on that system. I touched on this earlier. I'll give a specific example probably when we get to the wharf use case about running that particular container on HPC systems. I have an hour, right, Eric?
Yes.
Is that right?
Yes, you do.
Can you tell me when I hit a half hour?
Remaining? Yeah, I will.
Okay, thank you. That would help. Okay, so Singularity with MPI, we actually talked a lot about this, so I probably won't go too much into this. I'll give the more specific example. Multi-node is more dependent on the system. Yeah, we talked about that. We've actually also talked about this more at length. We talked about the different container runtimes, so I can skip this. If you have any more questions on these specifics, please do ask. If you're setting up a, yeah, I will mention this. So for the cloud model, if you're deploying on the cloud, and in particular, if your multiple people may be running jobs on the cloud. So for example, you have a container, you want to run it multi-node, and you use some kind of orchestration system, possibly Kubernetes, and you deploy a cluster-like environment in the cloud, and you want to have multiple people be able to run jobs similar to an HPC system. That is when you need to start looking at users and the Docker container security for the users within the container. And then that's where you want to be much more aware of the Dockerfile best practices and some of their security concerns there. And there's also some controls for within Kubernetes if you're using that, or other managed services to deploy clusters to control security. So that's another thing to be aware of. Oh, I did.
Sorry.
Okay, sorry.
I have a question regarding MPI. I'm not sure if you know this, but just out of interest, does Singularity actually have special, handling for MPI, or does it simply forward the environment variables that are set by MPI run?
So I'm going to cheat and pull up their website, but I do know the answer to your question. It's a very good one. And this will explain what I was asking earlier about bind versus. Are you seeing the Singularity and MPI applications?
Yes.
Okay. So I think I shared this in the chat. I'll just share it again as well, so folks have it. This is a very useful page. I think they do a good job explaining. I'm not going to obviously read the whole page, but essentially Singularity aims to sort of naturally implement with the OpenMPI MPitch versions of MPI. And they have two models that they use. And this is also how they integrate to some extent with batch schedulers. Sorry, I don't know why that word escaped me for a moment. And so there's sort of two models. The first model, which is tends to be their recommended model. Actually, this is a helpful sort of summary. The bind model requires users to be able to mount user specified files from the host into the container. This ability is sometimes disabled by system administrators for operational reasons. If this is the case, your system on your system, please follow the hybrid approach. So it's really about, do you want to use the host system's MPI libraries, or would you rather have your own MPI libraries within the container and link them? And there are benefits and disadvantages to those, which are extensive. But essentially what you have is, with the hybrid model, you have a MPI library inside your container. And one of the examples I'll show later is actually with Intel MPI. It's not one of the supported MPIs, but it does actually still work with pain and with pain to set up, not to run. But the Singularity container has the Intel, or sorry, in that case Intel, but the MPI library that you would like to use. And outside of the container on the host system, you have another version of, well, hopefully the same major version. And it can be, the version in the container can be the same major version, and it can be newer. And I've never verified, like say you have a MPI version 4 of whatever particular library you're using. I've never verified that you can actually use MPI 5 or something like that. Just throwing out random numbers, not a specific example. But I do know that it can be a different major version, or sorry, different minor version, because we have tested that. And it also depends significantly on the system, what's implemented, because there's, you might be dealing with your MPI application deals with uses a certain feature of MPI that's based on a certain version, and the host system has a different version. That can get into other issues. But essentially you run the MPI exec command on the Singularity command, and then the scheduler ends up using the process management daemon, or sorry, the system uses the MPI process, calls the, sorry, I'm looking at stuff too. MPI then calls the process management daemon. And this connection happens between what's in your MPI library inside the container and the host MPI, and sort of works throughout, is I guess how I would summarize it, and works with Slurm. And yeah, they talk about the drawbacks in brief. And they give a test application you can actually try out. And they talk about MPitch with a hybrid container and OpenMPI with a hybrid container, and a little bit more about running the MPI application. And then the bind model is where you actually build the container empty of an MPI library, and you call MPI from the host. And so similar, you would call MPI run on the host, and it actually treats it as if the MPI and the host is in the container as well. It's you map the paths, and it looks like, yeah, there's a definition file example, but when you're actually running the application, yeah, this is what I wanted to show you. You do an MPI run with a number of ranks, Singularity exec, and then you do this bind flag, and this is the directory to the MPI host libraries, and then your image and your binary that you want to run. So if you're using, say, dice.py here, and you have the host level directory is here, and then your CIF, which is the Singularity image format file there, then then it's dice.py as after that. And so that is what would get the MPI command run on it within the container, but the MPI library on the host is what would be used. What you're choosing between really depends on your system and how you've set up your container. And it's generally recommended that you look at the system, and this is the super important, irritating thing, in my opinion, about HPC MPI applications with containers, is it completely reduces what's portable. If you're running on specific HPC systems and you design a container for that system, which you sometimes have to do because of the specialized hardware, as I've mentioned earlier. Whereas with a cloud container, it can usually be a lot more portable, and running containers in the cloud and trying to move to HPC or vice versa is kind of an active area of bottleneck, I'll call it. I hope that's.
Yeah, so you touched upon, portability before. So I guess the bind model, you can make it portable if your exec command is actually to first build the whatever you're running, which is of course not always feasible, but if it's a smallish program, then you could conceivably build it first within the running container, link to the host MPI, and then you would get a somewhat portable image that way, I guess. But that's not feasible if the build takes several hours, of course.
Right, yeah, and I would argue that that's kind of a nightmare way to make it portable. It is a good point. You could hypothetically make it extremely flexible, with the exception of those drivers for specified hardware that I mentioned earlier. So for I guess I'll use the example now, but on TAC's Stampede 2 supercomputer, it requires the Omnipath interconnect libraries, the Intel libraries, and you have to use the Intel MPI library or Mvapich 2. Yeah, sorry, Mvapich 2. Those are the two options that they support for multi-node, and so they basically recommend you use our base images, or you don't, have a functional multi-node container.
Yeah.
And so that is impossible to make portable. You cannot make it portable unless you somehow set up a logic to just not use those, to detect the Omnipath hardware and only install to your container if it's necessary, which would be a whole lot more extra logic. And there are ways to do that too. But again, this gets back to that idea of development versus production. So if you're developing, that might be a fine method for portability, but for a production container, in order to get an optimally small container, ideally, then you really want, you don't want to be building on the target system. Yeah. And this is actually this is a really good point, that I always think about how will I include this in the tutorial. So I just figured out how, thank you. This philosophy difference between cloud and HPC is interesting, because containers are so easy to move, move around in the cloud, portability is just kind of assumed for a lot of cloud type deployments. And for HPC, portability is not assumed. It's almost like most of the way software is designed for HPC is for to eke out every bit of performance on the target system that you can. And so you compile, so for the weather modeling application we're going to talk about, WRF, you compile on the target system, as that's the standard practice. It's not standard practice to build ahead of time and then deploy it in multiple places freely. So portability in design is a real pitfall in HPC containers. And so this really comes up here, where if you're trying to do, even if you want to use the host MPI and you can find some way around, not putting MPI in your container and compiling, you really have to compile on the host system, or sorry, on the target system, even if you are to build your container. And that actually can be, there's another downside there, is if you have an allocation on a system and they require you to submit a job to use the container runtime. So for example, Stampede 2 requires you to submit a job to run Singularity commands. And that's just a security reason. And so you're actually using up your allocation to build your container, and your container build might not work the first time or the first 50 times, depending on what you're building. And if it's an HPC application that you're trying to tune really well to the system, it might be a lot of iterations. And so atmospheric scientists using WRF are often accustomed to compilation nightmares. And so a container that would be portable would be wonderful. But compiling on the target system is common practice, or even in some cases best practice. And so then you're eating into your allocation, just trying to compile your application, which could also be true if MPI needs to be, if you're testing, you might be eating into it anyway. But yeah, for just compiling your application, then eating up your allocation, that just seems very painful to me, on top of all the pain of, if it doesn't compile, it was time wasted. And WRF is often not a quick compile. So yeah, that touches on.
Yeah, that makes sense. So I guess the only thing containers in HPC really solve is dependency management, right? Except for MPI maybe, but that's one of the big problems that I usually have, that is that module systems don't offer certain combinations of packages that I need. And then if I had a container, I could at least ensure that those are always present, except for MPI.
Yeah. It definitely solves dependency management, which is a lot bigger of an advantage than it is in industry, arguably. But I would say it's not the only positive. I realized how negatively I was sounding. Not every system has these portability pitfalls. But I just wanted to say that if you say you wanted to design the most portable container across HPC systems and you weren't even interested in cloud, you could hypothetically find ways to account for some of these things, but ultimately you're going to have to build on the host that you want to run on. And that can be, tedious beyond the normal tedium of building on that host. So there's containers add, in some cases, a layer of complexity that is inconvenient if you want portability. But portability, I guess my argument is that HPC systems make portability difficult, period. And that's why HPC containers are difficult for portability. So if you're thinking, I want to use a container for my HPC application to make it portable, it's not that simple. It's possible, depends on what where you're running, but it's not that simple. But I also want to say that a lot more systems are becoming more flexible with containers, finding new solutions for making portability more reasonable for their users. So the specialized hardware situation is kind of frustrating, but if you're the kind of person who can build a WRF container, then you can build a WRF container on this target system. And to some extent, you still get the benefit of portability of the Docker file, because you can remove the drivers you don't need, or you can start from a different base image. There's a lot more flexibility there, which I can get into when we actually look at the WRF example. Have I got, I think I've hit over a half hour, haven't I?
You are just now coming up on it, so.
Oh, okay, sorry, I misinterpreted the time. Sorry,
You're in good shape.
did I cover I was talking to Philip, right?
Yes.
Okay,
Yeah,
did
yeah.
I cover all of the questions that you had?
Yes, thank you. Sorry for going on such a tangent.
No, this sounds like a tangent. It was all to some extent planned material. I just said it in a different order than my intended plan.
Okay.
Which usually means that's probably the order I should have planned it in. So next time I'll probably say it in that order intentionally. It'll seem more seamless. There's a lot of things. So the HPC container space is constantly moving, and there's a lot of things that I have recently sort of wanted to add to this tutorial. So this is perfect. It's giving me a chance to sort of stretch my legs in this in the way that I'm explaining this that I haven't necessarily before. So forgive me for if it's not so seamless. I think what I'll do actually, I'm just going to share my my whole desktop so that I can kind of switch between. Did I share the wrong one? What are you seeing?
We're seeing slides. Now we're seeing your browser.
Oh, okay, it switches with me. Okay, all right, okay. That's useful. Okay. Yeah, I'll do that. So I'll play from this slide. This way I can jump back and forth between browser and slides more easily, if that's okay. All right, so I hope I haven't intimidated you all away from HPC containers, because there are some really cool solutions out there we want to talk about. But the reality is that there are some difficulties as well. Okay, we talked about that. And I'm just going to say, Thomas or Tim, if you have any specific questions, please do feel free to say so as well. I did talk about this. Okay, sorry. Just catching myself back up on my own status. Okay, so the, oh, right, I did include these vulnerability scanning. Okay, I just had my own slides in the wrong order. Okay, so Singularity security options. So this is an interesting thing. The way the security models of Docker and Singularity are just inherently different, which is where you get the root differences. Excuse me. The major thing I'm trying to say here is that Singularity security options differ entirely from the types of security actions you get in Docker because of sort of the divergence of what they're trying to offer, but there are also a lot of overlaps. Excuse me. So there's Linux capabilities. Comment is talking about how certain features of certain applications require different Linux capabilities, and Singularity starts, with minimal, minimal access to sort of extra stuff, but there are ways to securely add certain permissions, and that's covered in the documentation. They also offer encrypted containers, and there's a lot more in that space that you can check out. And Docker sort of also has Linux capabilities as well. In particular, this comes into play if you're working with things like profilers and GPUs and things like that. One place that you may need to look at this is extending the shared memory size in the cloud if you're running a Kubernetes cluster. We did end up changing the shared memory size on our Kubernetes cluster for recent WRF deployments in the cloud. So that's just something to keep in mind. This is the paper I mentioned earlier where Eric and I deployed his virtual cluster, self-scaling cluster. And One of the things I haven't harped on too badly here is reproducible containers, which is another thing. This is a general downside of containers, in my opinion, is that they offer the potential for such wonderful reproducibility. And one of the biggest pitfalls in research is things aren't done in a reproducible manner. And in this case, we're actually talking somewhat more about repeatability as much as more so than the reproducibility in the sense of being like numerical stability. You can recreate the same numerical answers. Because with each individual, some applications like WRF, each individual run, even on the same system, same initial conditions, can have some slight variation. So I'm not talking about that level of reproducibility, but they're reproducible in the sense that I hand you a container and my data, and you should be able to run my application and at least get very, very similar results. But if I hand you a container image and you want to change it in any way, shape, or form, such as add a dependency or add your own software, or just change where a file is located, and you rebuild, containers often are not at all reproducible in that sense. And so one of the things that we've done is start exploring different ways to make containers more reproducible for the build and deployment. And this project has recently been expanding to include automated deployments, we're hoping quite soon, on various Exceed systems and verified testing and container images. And so this is our paper about sort of the mindset behind that project, how we got started. And here's kind of a brief overview of what we're doing there. Not all of our containers use Nix, but the Nix, so Nix is an operating system. Nix OS is an operating system. Nix is a package manager. And there's also the Nix language it's a functional programming language for writing basically package builds. So not all of our containers use Nix. It can be an added layer of complexity if containers are new to you, but if you are curious about that, that's the paper to go to. And the general process that we do have, though, whether or not we use Nix, is creating a Docker image, converting to Singularity. Singularity Hub is no longer available. I need to update that image. We were deploying to Singularity Hub, and we were also deploying to Docker Hub, but then you can use either version. We still create a Singularity image and test on Exceed resources and in the virtual cluster, such as the one you are running in today. And then we've tested in other clouds as well, public clouds and Jetstream and private clouds. And I'll actually quickly, I have the repository for that open, I believe. So the container template library. We have a bunch of base templates and software templates you can get started with, and we're going to be expanding this more soon, and certainly look for forthcoming updates there. There is also, I can't remember if I pulled up the Exceed Docker Hub organization, but that can be another place to go. So if you go to Docker Hub and you search for Exceed, you should see our containers there, and there's going to be more activity again in that space. Yeah, so the Exceed organization, and we have some containers here. So that's another place to go. And all of these should convert to Singularity. And yeah, okay. I've talked a little bit about orchestration. Actually, this paper here, we tended towards Terraform and Ansible for deploying clusters in the cloud. We've deployed with the virtual cluster with Ansible as well, and more recently been doing a lot more with Kubernetes. I don't have a link yet, but there will be a preprint up very soon on Archive about the Kubernetes work we've been doing with WRF, so look for that as well. And if anyone is specifically curious about any of this, I'm not trying to toot my own horn. I'm just trying to say there's a lot of different things you can do here. So trying to give you sort of a taste of what's out there. And I can also link you other papers if you're curious about different types of cloud deployments that I haven't talked about or I haven't tried. If you're curious about the managed systems, let me know. I can point you to papers about that as well. So Docker Swarm is what this image is about. That's another option for deploying containers, orchestrated containers in the cloud. And that one is usually not the default for HPC type orchestration, but just be aware that it's out there, particularly for simpler applications. It can be nice. And we've done simple tests with that as well. So that's something to keep in mind. One of the interesting things I really like about Terraform, I'll plug it briefly, is that Terraform is relatively newer in industry, but also in, I guess it's not super well used in the research space. And the major reason for that is what Terraform does well, in my opinion, is multi-cloud. And so you can set up scripts that functionally deploy Kubernetes clusters or set up VMs with Ansible or do any number of other things, or purely Terraform oriented provisioning. And a number of variables are all that are different between different public cloud providers. So if you're interested in taking advantage of multi-cloud deployments, Terraform is a really powerful tool. If you're not, if you're married to a particular vendor, it's utterly irrelevant. It can be useful. It has other nice features, but that's sort of the main selling point in my opinion, for HPC style clusters in the cloud. Oh, yes. Before I move on, are there any questions? This is a joke about cloud. Okay. Seeing no questions. Oops.
Just a note, Pete, you're at about 20 minutes left.
Okay, cool. So there's a lot of things I can say. I want to cover Wharf as an example, and there's a lot more I can say. So I'll probably do a quick overview of the other things I was going to talk about, and then ask which areas people would like me to dig a little deeper into. And still feel free to interrupt, ask questions. Okay. So actually, I'll start here. So if you go to our container tutorial, there's an eScience 2021 repository, and there's a bit of a README here that covers the different things we've gone to. If you go to the very end, actually, there's the further references. I know I've done it out of order. I'll probably fix the order later, but at the very least, the further references page is where I'm going to work off of. I wasn't sure how much time I would have to get to everything. So at the very least, you have all the references here. The very first thing I want to point out is that we are not the first person to ever develop a container for Wharf. And the so NCAR's Docker container is very much a development container. And actually, they walk you through compiling on the target system as part of their tutorial. And so this is their Docker file, just to give you sort of a brief overview of what this looks like. You can see that they do set up environment variables using the env command. They start with a CentOS image. You can see the maintainer, and you can see they're using yum to update a whole bunch of libraries. And you can see immediately before you move forward which compiler they're going to use, because they're using GCC Fortran. And that means OpenMPI, if I can find it in here, is on the list. But they, you can see the, sort of some of the base tools that ended up needing, like Jasper, and they use zlib. So there's a bunch of dependencies of Wharf that come much more easily if you're using the GNU compiler. And so that's where they're grabbing them. And they set up a user, a Wharf user, and they build OpenMPI. Oh, right, sorry. They do the actual build of OpenMPI. And I think there's a reason for that, that they chose to do that. But then they build, so they start building Wharf dependencies, and they set up an environment for you to be able to interact with the container. And yeah, there's C and Fortran libraries that have to be compiled for Wharf, and they set up an interactive container shell and they download Wharf and they download WPS, and then they walk you through compiling for your system in their tutorials, and they set up some nice tutorial treatments. So there's two main containers that I was gonna say, so I am basically the maintainer of these. So if you have specific questions, you can point them to me. Oh, I did already open that, I apologize. But there are also other folks that were involved in this as well. Essentially, we first, working with the Wharf researchers, they're doing atmospheric science, studying making sustainable wind farms off the coast. And so you have gusts of wind and you have waves and all sorts of different parameters you're trying to take into account. So they actually use custom proprietary software as an add-on to Wharf. And so their containers I can't actually show you. So these are not, the ones that I'm showing you are sort of base containers that we made publicly available so other Wharf users can use them as they wish. But the proprietary code is later added in and compiled. And there's some changes inherent in those containers. So these real science has been run with these containers, but not these specific images, if that makes sense. The other container I will show you we've run CONUS benchmarks, which are the standard continental US benchmarks for Wharf. And so we started with 3.8.1, which is an older version and requires patches. And so this repository you can actually go through and you can see it was previously hosted on Singularity Hub. It is no more. It's still alive in the archive, but not in the actual Singularity Hub itself. And so on this in this particular repository, we were testing out various locations. So we did do some running on Stampede 2, which is one of the ones I mentioned earlier. If you are running on an HPC system single node, you can use whatever MPI you like within your container. You don't have to bind, mount, or use the hybrid model. If you're using MPI multi-node, that's where those concerns come in. So you can actually use this GNU compiled container that we've created and run single node Wharf on Stampede 2 all day long. You only come into these issues when you that I mentioned when you run multi-node. And so you can see that this container is set up again with GNU. Just to cover real quickly, and there's a lot of setup that goes into making a nice environment where you can actually recompile. So this container aims to be able to compile. This is a development container. And this container was used in development for years, actually, on Aristotle by Wharf researchers. And whenever they needed to add in a patch or use a new piece of proprietary software, they would simply recompile within the container. So that's sort of a design difference. And then this Wharf version 4, so actually I'll start at the base, at this base repository. This is still to some extent a work in progress, this repository, I should say. So documentation will probably be added a lot more very soon. But right now it's kind of has the core components that you'll be looking for. Singularity is actually on a different branch. But right now you can see that it's set up to run the CONUS benchmarks. There's a particular use case they picked. And so you can actually get the data yourself. And it uses the pre-Thanksgiving winter storm of 2019. There are 2 different levels of benchmarks. You can do the reruns. You can actually compare to CONUS, or sorry, to NCAR's system. And we also did a bare metal Stampede 2 setup. And so this is this has kind of some instructions on how to set it up. And actually I need to add some documentation, but essentially if you wanted to run on Stampede 2 bare metal or use the Docker container, everything that you need is in this repository. So you could run Wharf yourself. So the first thing I want to mention is that this this container is based on an Intel public container. Give me just 1 second. Okay. And this, oops, I forgot. No, sorry, I opened that up in a different. So this Intel, the Intel One API HPC toolkit, if you are unfamiliar with it, is a toolkit that Intel provides. Sorry, I'm trying to find the right tab. I have too many open. Is a container set of container images, both Docker and Singularity, that Intel has provided to include the C, Fortran, C++ compilers, an MPI library, the traditional compilers that were previously closed sourced and cost, and now are made freely available in Docker and Singularity images. They also provide the toolkit separately if you want to set up a bare metal system with it. And so we used these, are my Slack images popping up? I hope that's not annoying. So we use this base image, which is very large actually. So it starts as, because it includes all the compilers and the MPI libraries, and it actually includes vTune and other profiling tools. This is kind of a great development container to start from, but it starts out around after you uncompress it. So when you pull it down, it's like 7 gigabytes compressed, but it ends up being around, I think, 23 gigabytes uncompressed, which you have to account for if you're trying to move it around. And then adding in the various WRF dependencies and WRF itself, it ends up around 25 gigabytes. So the WRF dependencies, excuse me, and libraries are only account for about 2 gigabytes of the container. But this container, these sets of containers, you can go to their GitHub repository, One API containers, and you can look at their various images, and they have documentation, and they have other, base containers. You can use a base toolkit, runtime libraries, IoT, DL, AI, et cetera, et cetera. So it's a very interesting set of container images to check out. And so that is where we started. And one of the next tasks is going to be making a more minimal production container. But we have run some level of production runs even with our development container. And so that's been very, very interesting. But if you wanted to download this particular container, you could right now on Docker Hub. Our Docker container images are all on for this particular project, are on the Cornell CAC Docker Hub, and WRF is listed here. And actually, I think I have it open. Yes. And so the particular image I recommend is the latest one, which I will probably later change to also be latest. I have not right now, but you can check out our GitHub repository or the image itself. But one thing I wanted to point out about this whole process was that we specified, so you can specify a particular SHA hash of an image in Docker Hub as your base image. And so that's where we started, and we get a very specific, so unless they update this particular tag, which they can, we will always get this version of the Intel base image that we're working with. And so this is probably the most complicated, arduous container I have ever built, because WRF is just sometimes a bear to compile. And by default, the MPI libraries are not enabled in this container, and so you actually have to enable them. There's a lot of, one of the downsides that if you're not a sysadmin and you're not really sysadmin minded, it can be a little bit of a hurdle to try and understand all the things that are needed to add to a container in order to make MPI function well within the container, particularly if you're doing the hybrid model. So set up to configure the Intel MPI libraries, there was extra steps, and we did these because we were planning to convert to Singularity and also to use this as a Docker container. We did some nice more interactive shell type stuff that you could probably skip. But then there's, installing the libraries and dependencies. All of these dependencies are compiled with the Intel compilers, and Wharf itself is compiled with the Intel compilers. And you can run this Docker container yourself. It will not run something. You have to give it data and run Wharf commands with it, but you can hypothetically run any Wharf execution that you would like to with normal Wharf 4.2.2. It doesn't have WPS, which is for data processing, but that could be added as a next step. And so the major, so we did run the CONUS benchmarks. There are scripts inside the Docker folder for running CONUS with this Docker container. So if you would like to try something out, this might be a good place to go, and that could be fun. And if you enjoy that kind of thing, I do recommend the tag. I should update this. That's the old tag. The one thing I will say is that because of the differences in Stampede 2's hardware, this Docker image, when you convert to Singularity, will not run on Stampede 2 because it does not have those drivers. So I may end up making a different repository that has the TAC drivers and sharing that as well. But if you want the bare metal comparison here, it's in the Stampede 2 directory. Let's see. If you want to look at Singularity, again, this won't run on Stampede 2 per se, but this hypothetically will run elsewhere. But this is sort of the base. So if you're trying to set up, this will run on a VM. I have tested that. But as far as like if you wanted to run MPI on another system, it might depend on the hardware of that system. But there's some information here about kind of how you would use the, and some of this stuff is Intel One API HPC Toolkit specific. So if you wanted to set up a system to run this container or any of the Intel One API HPC Toolkit containers, and you wanted to use Intel MPI, you would need to do some of this setup, and you have to actually build the container. We don't have this image stored somewhere right now, just because of its size. It can't be stored on the publicly available repositories. Trying to think what else I could say. The CONUS benchmarks include some interesting comparison scripts you can use. Again, Singularity is on the Singularity branch, so if you're looking for that. And I did include, excuse me, they have a Python tool. So if you run their CONUS restart, you can do a quick comparison, and you can actually, there's a README about getting numerical stability. So I did include some base results about running the CONUS 12-kilometer benchmarks, single node, and then multi-node for the 2.5-kilometer benchmarks. Just, it's a good way to look at numerical stability. You can also use these comparisons within the container. I don't think I added those results here, but I should probably do that later. But just kind of a simple way to check, like, are you getting numerical stability? And we did see that we were getting numerical stability, so that's a very cool result. We also did larger scale simulations with the private container. I think we did one major run that was about 5 or 6 days of actual compute time, and graphed the differences between numerical results and found everything was well within statistical good statistic ranges, and furthermore, performance. So one of the main conversations about Wharf containers is it worth it for performance? And so there are actually a number of, I think they're included in my doc. Let me make sure. Oh, okay. I don't think I have them in the doc. I will make sure to add them, but there's a number of performance papers you can look at that talk about the differences between various container runtimes or VMs and runtime and containers and bare metal and containers. In general, if you're using bare metal with and containers, you should, depending on the container runtime, you should see some difference. It's, as far as I can tell, it's almost always smaller than virtualization in general. And sorry, I'm rushing through this because of time. But then also just the major difference is that you're probably going to get better runtime with Singularity than you are with Docker. If you're using Docker in the cloud on a virtualized system already, you're probably going to get, for HPC, there are a lot of other performance concerns that are probably going to impact you a lot more than just using a container will. So if you're virtualizing already, particularly in the public cloud, you're dealing with tenancy issues and network latency issues. And so depending on your configuration, there's a whole bunch more concerns that will affect your performance, degrade your performance potentially. If you're eking out every possible performance, it can get really expensive. Every possible bit of performance in the cloud, it can get very expensive. There are some reasonable solutions that are not expensive. And then if the container itself is your bottleneck, that would be, I guess, to some extent surprising, particularly with an application like Wharf that tends to be, depending on the simulation, depending on how you're using it, could be compute bound, could be memory bound, could be IO bound. And so there's a lot of considerations. And so for the actual cloud deployments, we use Terraform and Kubernetes deployed clusters in AWS and GCP. We did deploy clusters in Azure, but we didn't run Wharf there. But essentially just doing some testing there and comparison across those three clouds. There are so many various features you can use to speed that up. And ultimately, it was more a matter of, okay, what type of file system additions, how much does that cost? You're in this sort of matrix of possible options that you can optimize for. And the added, like the difference in performance degradation from containers comparably is smaller and much less of a difficulty when you think about ease of use. So if your ease of use matters to you at all, containers are much easier, and add the benefit beyond what the performance degradation would be. And the researchers we were working with definitely feel that, probably because we helped them by making the containers. They didn't have to make them themselves, because it is some effort making the containers. But then also, there are other bottlenecks that just come into play, that having the convenience of the container and the portability that it provides can just reduce that, reduce the importance of that. But it's definitely still an ongoing area of research, and we are intending to write more about that. So that is as much as I will probably say about our particular performance experience for now, but look for more forthcoming research. I have other references on here. We didn't go into GPU applications. There are some examples of some, GPU applications in our container template library, probably to be expanded more in the future. Let me get back to the tab. Okay. But certainly here's a bunch of other references as well. Oh, sorry. Yeah, I did link it. And then if you're interested in GPUs, and then we've had some folks interested in R containers. So there's some links there as well. And do I have time left? Does anyone have any questions?
Hi, everybody. I hope y'all had a good lunch break / possibly dinner break. So we're here at our final section, and I'm going to let Suresh go ahead and take over and talk about containers in the gateway world. Unless we want to wait a little bit to see if we have more attendees coming back. I know we're just now at the time we said we were coming back. I think this may be primarily for the benefit of the recording.
Thanks, Eric. Let's give it a minute or two, see if anyone else would like to join in. I know it's also getting too late in the European time, so maybe we can end a little early. So let's see how it goes. So any questions on so far what you heard so far? Before we get started, we will be doing a little bit of a context switching here. So far you've been playing a lot on the command line and learning about containers. We'll just introduce a new topic, the science gateways, and then come back into connecting that back to the container world. Any questions or comments?
Actually, I do have a question
Sure,
regarding portability, I guess, again. Namely, I've been thinking about creating a container image that I can use on 2 different systems that I'm working with. And trouble is that one of them is x86 based and the other one is Power 9 or Power 10.
Oh no.
Yes. So my question is, do you have any experience in that regard? And yeah, does that solve any, like, does Singularity help me in this case or not?
It will help you in the sense that you can have one build file for both systems, but you'll have to build 2 separate images to support different architectures like that, is my very short answer.
I mean, as we discussed already, you will have to do that in most cases anyway, right? With MPI and so on. So I guess as long as the dependencies work, then it solves 90% of my troubles.
Yeah, and you can actually build an image for a particular architecture on a different on top of a different architecture.
I was going to ask, yeah, because you said you need root to build a Singularity image, which is a problem because I don't have a Power 10 machine with root access. So
yeah, you should, provided that you have a base image available that's been built for Power 9. You should be able to continue building your actual image from the original Power 9 image with your software built into it on like an x86 machine.
So does that spawn a VM internally, or how does that work?
You know, I'm not sure. It's something that would need testing. I've run into that sort of thing in the context of someone that needed a 32-bit application on a 64-bit host, and it actually didn't solve their problem because you can't run a container built for a different architecture on top of you can't run a container built for, say, Power 9 or a 32-bit system on top of an x86 64 system.
You cannot?
Right, you can't run them on different systems, but there is a flag when you build to target a different architecture.
Okay, yeah.
So I don't know how the internals of that actually work.
And somewhat related then, do I need, for just building a Singularity image, do I need Docker installed as well?
No, you do not need Docker installed as well, because Singularity will pull and convert any images that are Docker based beforehand.
Okay.
And those tools are completely separate.
Great. Thank you.
Yeah, we didn't talk about this a lot, but you can build pure Singularity images without Docker at all. So.
Yeah, but I was thinking if I base it on an existing Docker image, maybe it needs Docker installed as well or something.
If you use a Docker base image to convert, yes, but you could look at a Docker file and just change the, like, copy paste the commands and edit them into a Singularity definition file.
Wait, Pete. He doesn't need Docker installed to just pull down a Docker image using Singularity.
Right. Yeah. No, you don't. You don't. So if you want to use a base image, you do not need Docker installed. Sorry, did I say that?
You said a yes that made it sound like that's what you were saying to me.
Okay. I apologize.
I may have misinterpreted.
Oh, no, it's good to clarify. No, I didn't mean to imply at all that yeah, Singularity is a distinctly separate tool. It intends to be interoperable, but once a Docker image is stored in the registry, it's separate from the Docker runtime itself, and Singularity just pulls it from the registry.
Okay, that's cool.
Yeah.
Yeah, Thomas, looks like you have a question. We can't hear you if you're trying to speak.
Oh, I see the green border, but I don't hear anything either.
I'm curious if you're using the web version, maybe you want to try the Zoom, Thomas? I meant Zoom app.
Can you hear me now?
Yeah, barely, but though. Can you see if you can speak closer to the mic?
Can you hear me?
Yeah, it's getting better.
Yes.
Yeah,
Okay,
please.
I go a bit closer. So my question is the following. So I see a kind of evolution from original heavyweight virtual machines, then to container, which is a strong focus of your tutorial. But in the cloud era, there's like this next step. A lot of people move towards serverless computing, which allows the application developer to have a view that's closer to the application, whereas containers is a bit more system administration view. And here with serverless computing, which kind of it doesn't replace container, but it kind of makes it disappear from the application developer. And it's much more lightweight. You're much faster to deploy and run a function compared to a container. Is this something completely complementary to what you're talking about, or is this somehow an issue for the work you are presenting? Serverless computing, the serverless function view, as opposed to a container view.
I actually do have a colleague who created a Wharf container to be used with serverless functions, and does full Wharf modeling with serverless options in AWS. The real, so I wouldn't say they're in conflict, no. You can use a container with that kind of tool. You could go without containers, but the difficulties are different. And the major downside, I sort of touched on it, but it didn't say it clearly, so I'll say it clearly now. The major downside that I would see for HPC in the cloud in that way is that you are really locked into the particular vendor's options. And that may be perfect for you if it works for your application, and that's a good workflow for you. That seems like it, the right thing to do. However, if you want the flexibility and the portability that containers provide, it's really beneficial to not have the vendor lock-in that makes it less portable, I guess.
Right. But there is open source solutions, right? Like OpenWhisk or OpenFaaS. Also, the group of Ian Foster, I think they do a lot of work with serverless computing in the context of HPC. So it's not, you don't have to go with Google, Amazon, and so forth. You have open source solutions that kind of, I wouldn't consider blocking of your work. I see the bigger change from container to serverless function, which really pleases me, that it lets you switch from a system administrator view to the application developer view, because the container is still there. Most of the serverless platforms require a container, of course, but you don't see it as application developer. And I think this is an important step forward and widens the class of people that actually work with that technology. That's what I like with serverless computing. I consider it's the next step after containers, but you rarely mentioned this kind of technology. Probably it's more visible in the cloud edge context and less so in the HPC world.
Yeah, I mean, like I said, for the Wharf application, the colleague of mine who did deploy that kind of workflow was a significant investment for him, and it was a lot of support from AWS, AWS specific tools. I'm a little bit less familiar with the open source options you mentioned, I'll admit. So perhaps that's something I should spend some time learning about, and I'd be happy to get links from you. But yeah, I think most of the cases that I have worked on with containers have been driven by researcher need. And so they wanted to do something, and we found a way to do that for them. So even the cloud HPC in the cloud that I have worked on has all been researcher driven to some extent. So that would be my explanation for why I've chosen that path. And as for why we've chosen not to focus the tutorial on that, I guess that's one way you could go, and that's, you know, we stuck with the expertise we have.
Thank you very much.
Yeah, and let me connect that to the talk with the last bit of a tutorial. Thomas, yeah, thanks for hanging on. I know it's late in the day. And yeah, how are you doing? Like, you know, it's been a while, waiting to see you back in DC.
Yeah. Yes, very good.
So let me start with, like, you know, when my yeah, as Peter said, yeah, thanks for your questions. And yeah, I'm sure I haven't seen your papers lately, but I'm sure you do some of this stuff in your Ascalon and Apollo frameworks, right, Thomas? Yeah, I haven't.
Yeah, exactly. So actually, it is very much research oriented, but more like, you know, in the IoT edge cloud world. And of course, there the people try to get out of vendor login, and that's why there's quite some interesting open source solutions. And so people work less with scientific workflows, but it's more like enterprise business applications, but still very much research oriented, at least in Europe. A lot of money goes in there, you know, how to map, deploy, how to build applications with workflows in this world. And serverless computing is really big. And some even drag it over to HPC world, but in the cloud distributed systems world, it's very important.
Yep, I think, yeah, that's right, Thomas. You rightly pointed out to the edge-like scenarios. Like, you know, here we have at IU, Professor Martin Sweeney and group have been exploring how to use edge computing in as a way to do campus computing. Like, you know, for example, they have a new project, like, you know, which will be launched soon. It happens to be called Indiana, but like the basic idea is, how do you move applications out of a campus into national infrastructure? And they've been actually promoting like a serverless model. It's very, as you can see, it's like, you know, it's hard to parse that together, but like, and I think yeah, we'll wait for Martin to give an eScience talk sometime. So first, at least let me connect to this tutorial context for the rest of the audience as well. So yeah, as Thomas asked, like, you know, for example, like, you know, how can we take these applications and then connect it into the other worlds, like where applications change or applications are not, like, you know, very compute intensive, but like, you know, need to be invoked quite a bit on request, like in the case of the main serverless paradigm, where as the data comes in, you want to invoke your application many times and things like that. So an example how I'll connect this to my next talk, a gateway one is, we have seen the main part of the last module is, we have seen logging onto it, like in this case, let's say replace that with a Jetstream cluster, and how we used the GIF generator here to run an application with Singularity, and we'll go to that tutorial. But like and there's other piece of our infrastructure where we use these containers heavily, which is the data parsers. So unlike these compute jobs, which take a while and you need to run through Slurm jobs, data parsers are something, let's say, like, you know, again, it's a busy diagram. I'm not walking through the whole thing, but trying to give some context here. Let's say, like, you know, we black box this and say we run a job and you get data out of the job, and you need to parse those input files and outputs to go deeper into the metadata. And then, like, that's an example area where those parser codes change often, and then there are lots of them. And let's say you're plugging in this to a general purpose infrastructure like workflows or gateways and so on, you'll have lots of the file types to come in. So that's an example where you can containerize those parsers. Those parsers could be coming or built over well-known like in some domains like OpenBabel, like infrastructures, like which can parse lots of chemistry files to lots of in the biology and like bioinformatics space, those parsers change often. So essentially you write a parser, you containerize it and deploy it into a container orchestration framework. And for every new file which you applies, then you run through the parser, extract a lot of extended metadata out of it, and then make it searchable. So this is an example serverless use case. So here, my last piece for this tutorial is how can gateways take advantage of containers? And this is an example where if you have a lots of various lots of changing applications and you want to deploy it, and you can use that. Of course, you can do the standard model of running through a batch system, or in a serverless mode based on you're applying to lots of data sets. And there are other use cases I briefly mentioned during the introduction, very brief introduction earlier in the day. You can also run the entire gateway framework using containers, but that's a topic we are not going to today. So does that help, the context, or did I confuse more? Or I'll go back.
Yes, very interesting. It's very interesting.
Yeah. Okay. Thanks, Thomas. So yeah. Again, thank you everyone for hanging in there. So we will talk a little bit. We'll step back and talk about science gateways. But those of you who are using science gateways, I guess it's more of a word we use in United States, but in in some parts of other continents as well. But interchangeably, it's you can call it eScience as the name of this conference sounds, or workflow infrastructures and workbenches, and it's called differently based on the funding trends, I guess, or based on the buzz we catch on. But right now, it's one and the same, because it has a very broad definition. So I'll just put that definition up from Wikipedia. So science gateways are broadly the web interfaces and middleware that integrate various distributed computing infrastructure, which includes these clusters and various data resources, and the applications which are containerizing and the topic for today, and get the data out of those application execution and manage them in an easier, friendly way. So the big goal for science gateways is democratize science in some sense. So instead of for example, we've been going through this tutorial, we need to, let's say, follow the full life cycle of take an existing Docker image, convert it to Singularity, but now you need to serve users, a chemist and or you take any field, as we have on the call, some physicists and so on. So if you have physics application, you can, of course, some domains like physics and chemistry are very well versed in using these computing scenarios. But let's say you want to make them available so that early researchers or students or or you just don't want to do the full step of learning all these things, logging to a command line, getting accounts on the computing infrastructure, running through that, you can make them available through a gateway infrastructure. So I'll talk a little bit today on how that's there, and we'll go through a hands-on tutorial, but I'll introduce that. We don't have a very broad audience, so please interrupt me. If you rather prefer to hands-on, I can jump to it. Otherwise, I'll try to spend some time giving some more context here, and then we'll do a small hands-on exercise. So I was just saying this, the gateways are broadly anything where you're making it easier to work. And then you do that in lots of different ways, with targeted communities. So I'll start with, let's say, have an instrument, let's say cryo-EM or in any large microscopes and from telescopes to any large instruments, and you have data coming out of those instruments. And you would like to make that data analysis coming out of the data processing or analysis or downstream science with that the experimental or observational data easier. We typically build instrument-based gateways where you can wrap the applications which process those instrument data and tie it back to the data sources and make it easy to discover and execute them on resources. Similarly, large interdisciplinary projects, like let's say you want to do a weather prediction, and that involves bringing together data mining experts, data assimilation experts, so hydrologists who have soil models and so on, and combine that with atmospheric scientists the WRF example Peter was describing. How do you take these, start with observations like radar data and so on, assimilate that into a forecast grid and run it through a model like WRF, get the output and post-process set. That involves, but that by itself involves lots of sub-disciplines. So gateways can help or bring all those sub-disciplines together. And now if you take that WRF example out, so you can take the WRF example and say, let's say you're predicting a big storm coming in, and then you can couple that with a hydrology model. Let's say, okay, there was lots of rain, then eventually it will lead to floods and so on. So you can keep imagining that. You can keep jumping disciplines here to solve the larger problems. And gateways can bring together those complex disciplines and combine those applications. So primarily by abstractions. So let's say a hydrologist, without having to learn every nitty-gritty details about how to build WRF or how to execute WRF, with various and tampering with various nameless files, they can just use a gateway by simple point and click and get their model runs out. So that keep going on. The other example includes there is a campus cluster or a cloud infrastructure, and we can deploy gateways to make it easier to interact with a cluster with various applications and resources on those clusters. And similar will be the data-centric gateways. There is a big data repository, we can keep talking on various machine learning-based science use cases to data analytics use cases and so on. So, and you can build gateways, and some of the one of the example I was briefly showing. So you do a lot of computations, and how can we build data gateways so that we can provide all those historical computations and help users analyze the output of them and compare them against each other, how did my output change for a parameter, for a particular physics or parameter change, and so on. Similarly, the education gateways are heavily used to teach classes in HPC-oriented classes and simulation classes. Oh, sorry, my slides are going in the reverse. So what's the core of these gateways? I was trying to describe the gateways come in and apply for different domains. So what is a big common factor here? So it start out with, let's say, the resource centric. So the goal for gateways is how can we change, abstract this resource centric into a very science centric or user centric view without having to learn all the details here. So let's say, in this case, we have been using the Jetstream cluster and containers in Singularity, and how can we take advantage of some of those examples and then let the user just execute their scientific job without having to learn those details. So that's the kind of a goal. So how that happens, at the first level, there is a middleware which abstracts those details. Okay, how do I run with Docker? How do I run on a bare metal? And so on. And finally, how do you, whether it's container, how do we execute on a cluster? And we take that and we make an API available through that middleware, and that API, abstract that API and build a user interfaces, whether it's Jupyter Notebook or a web-based UI, an example which we will walk through today. And then finally have users authenticate to it and then use this infrastructure. Okay. So in this context again, as I mentioned a few times, I'll pause here one more time to see if you have any questions. So we, as a group, at IU, we run this middleware and portals quite a bit, and using this architecture like microservices, those services quickly get bloated up into upper double digits. So how do we orchestrate that? Is we can use containers for those, but the point today, the focus today is the scientific applications. We are not just talking about the gateway infrastructure, but I'll pause here if anyone has any questions on how we are using those containers for those running the middleware. But otherwise, we will stay focused on how we can take a scientific application like containerize, which had a hands-on exercises since morning. And now the last portion we'll see is, let's say you containerize that and push it into a container, how can we pull it out and run it from a gateway? So let me pause here and take any questions. Any questions on the using of containers in other contexts, or like, for running a middleware, or any other in general questions? Okay, we'll take that as a no and keep moving. So I spoke about this, so I'll jump ahead. So the first portion, is okay. I was talking about abstraction. We need to make, let's say, use a clusters like Jetstream, easily accessible. So and then same applies to the applications or the images. So the first portion, which we need to do that in a secure, controlled fashion. So there are lots of security details, and you will see that, as we do the hands-on portion. How can we manage credentials of these, let's say, in this case, Jetstream credentials, and let the middleware manage those credentials for us. But from the end user standpoint, just use your existing authentication mechanism, like your institutional identity providers, log in, and then have these security details already pre-configured in the middleware. Use that, and then submit those jobs and running. An example could be a Docker Hub credentials. If you want to pull in some private containers and so on, you could do so with this such middleware. So again, I'll skip the larger portion, but I'll emphasize one aspect on where we find as a gateway developers and administrators the containers to be useful. So if I take an example of a production gateway, so which actually I will switch my share here, and I can quickly do that. Yeah, I think so. Yeah, and walk through some real examples on how we use the production application. So CGrid is a science and engineering gateway. The principal investigator happens to be at IU. Sudhakar Pomadigantam runs this. You ran to this before. So CGrid, primarily for the science, it's a broad science and engineering community. That's what it stands for, the science and engineering application grid. But it's primarily used in the web for applications in the chemistry domain. And there are quite a bit of applications, and some of them, as we try to see, they are deployed on lots of different machines. So Philip was asking about the portability questions. Again, it's not quite platform portability, but still jumping from one cluster to another. For example, here, we'll example, if you want to make Gaussian available on multiple different machines here, each of these, I'll not describe them now, but it's a campus resource at IU, and to a high memory machine at Pittsburgh, and a high memory machine at IU, to a kind of a commodity cluster at San Diego, and to a kind of a more of computational workhorse in Texas Advanced Computing, MP2. These are all different machines and will involve lots of details on how do we build applications. So, and as you can quickly see, go back to the dashboard and see, the gateway administrator job quickly multiplied, managing all these applications on different platforms. So that's a big attractive solution for the gateway administrator to see, instead of figuring out how to run. And I'll quickly switch as an administrator and show some differences here. So let's say I'll pick a random applications here and say, in an actual deployment, let's say this is a Bridges to high memory machine in Pittsburgh. So we'll need to configure, all the modules we load in this. This happens to be not such of a big issue on this machine, but maybe some applications, if I go back and pick a little more complicated application where you have to configure lots of different modules, different dependencies, and it'll quickly get bigger and bigger. For example, here's an NX 5000 application. So you'll need to configure, for example, quite a bit of pre-job commands and post-job commands on how to, before you actually run the application, you need to, for example, move from files and so on. Some of this, like doing it on each machine quickly multiplies. So here's an area what we can do is in a gateway using containers, you can envelop all of those kind of descriptions and how do we wrap the applications into whether it's Singularity or Docker in the recipe, and then use that over and over again in other machines. So that adds a little bit of a portability. You'll not get the full portability as we're talking. We still need to do some work in going back to the base images and reconstructing, but some of the repeatable information, it helps to save them. So that's an example on how we can use containers in this case. So to just summarize again, so for gateways to manage lots of different applications on different platforms is one example. I was briefly pointing to the data example is another example how gateways use containers. So with those examples, let me go back. Switch again to my PowerPoint slide and say how, for example, like again, just summarize for a gateway app store, how we can use it. And secondly, let's say again, we are not dealing with it more or less on all HPC machines, we use Singularity. But let's say gateways can also abstract these details, like let's say one of the machine has Docker as a runtime, and a different machine you have Singularity, that kind of details can be abstracted, and you just show for the user, how, sorry, scrolling too fast. Yeah, so how for the user's point, just help them, just execute applications and not worry about specifying about whether it's a container runtime or whether it's containerized or not. So in the process, as we do, so the way these gateways abstract is if you take put the Singularity example into this context, in the gateway's context, the gateway takes them and abstract them into a few high-level steps, like authenticating, like getting the right data into the right place, and then configuring the resource environment, executing the job, monitoring its progress, and retrieving results, and so on. So we can take an instance of this abstract description and apply it to our Singularity tutorial, and how we do that. That's what we will see in the hands-on portion. And in each of these abstract steps are kind of you can consider as a sequence of tasks compiled together. And each of those tasks could be monitored. We will monitor progress, and then of course coordinating with the computational resources. And as those statuses come back from this backend resource, let's say we have seen in the earlier portions, we have interacted with the Slurm scheduler directly using Extron and so on. So we take those for the job itself, they are submitted, queued, active, and complete statuses. And if you take that back and then roll all the way to the highest level from the user standpoint, a user creates an experiment, and that experiment gets broken down into moving data sets or inputs to the right place, submitting the job, getting those statuses back when the job is done. Let's say this is our output GIF image, and then getting it back and then showing it back. So this is what we will see in the hands-on. So I'll briefly pause for any questions. If not, we'll jump right into the hands-on. So the URL we'll use for the hands-on exercise, I'll paste it on the Zoom chat. We can get to it quickly. Okay, I pasted the tutorial link. Let me know if you cannot access it or if you have any issues going to this URL. Just so that I have a sense, so that I'll walk through slowly. Whole are planning to try the hands-on. Philip, and I think we have at least 2 external attendees. Okay. Yep. Thanks, Philip. Yeah. Thanks, Eric. So we will first log into the gateway. So if you to do so as a first time user, so you can use your existing like an institutional credential. I'm not sure, like, we primarily focus on the US based institutions, like, in common, but the service we use, CI Logon, interacts with a federation called EduGain, which includes most of the European and other universities as well. So please search for your institution to see if you can log in. Okay, I see at least if Thomas is trying to log in, like, Innsbruck is there. I'm not sure, Philip, if you can find your institution or not. So if you cannot find an institution, we can go to a secondary login mechanism. But if you can find it, please find your institution and click log on. So I just previously logged in, so it should take me right back. But if not, like, if you're logging into your IDP for the first time, it might ask you for your two-factor authentication or other mechanisms you have set up, and then it should take you back. Okay, thanks for verifying that, Philip. Yeah. So what you just did is, like, what I was trying to show on the slide briefly, like, we used the authentication and just we did not yet authenticate with the cluster. You just authenticated with the gateway. Now the gateway I configured it so that everyone who logs in has automatic access to run this application. If needed, we can put filters there or add groups. For example, like, if your institution, like, if you have an institutional cluster, you can add your cluster and so make sure that only you are in that group, so that now, in addition to the Jetstream tutorial VM, you can also run it on your cluster, and so on. So we can do various types of authentication authorization. We'll be happy to talk through those details. And there was actually a tutorial going on in parallel to this one, where the details about how this all these security mechanisms works, like, is happening in parallel right now. So first, let me, like, briefly describe what I've done here. And then we'll come to the user mode. So you probably will not be seeing this version because I've logged in now as an administrator quickly to show this. So I've taken, like, let's say they take some of the earlier exercises we had. So we take those, the description. I create an application by I think I'll lean back on Eric's naming convention and spend some few minutes to explain how good of a person he is, maybe naming different things. So, and I'm even better, so I'll just follow the same thing. So, but I'm not a physicist, by the way, so I'll not apologize. So I named the same application as a Mandelbrot Zoom, and I've taken different inputs. Like, for example, in the exercise you have go through. So I'm just, like, an example. What I was trying to show, what I wanted to show you is, if you go back to this, the GitHub location, and we will start with, we'll assume, let's say, Singularity is built, and okay, actually, yeah. So the Singularity container is done. And then now we are talking about how can we wrap this application. So I'll first start focusing with, okay, as a user, what should I tell the user, what kind of inputs they need to give here. So I've taken, like, the wrapped, the containerized application here, and what the arguments application takes. And as a first step, I describe them. And I give it some description so that, like, and you will see that if you clicked on that, you've probably already seen that. So I'll give the argument and then some initial value, which the user could change and say, okay, this is a GIF application, and you need to give for it, like, how long in microseconds, how long you want it to be animated, and the number of steps you want, and so the number of images, thereby the number of images it's generating to, and then the zoom, windows, the window sizes here, and the initial value, the finals value of the zoomed up image, and so on. And then you can also give other parameters, like just like the runtime, the number of multiprocessing threads it needs to span, and so on. And I gave the output, like, where to be generated as, like, as to pass it as generated Mandel. So, and you will see that. And I give it a MIME type as an image GIF so that my browser can render it. And I'll also, I'm telling to this application, I'll need to also see the standard error and standard output for this. So with that, once I describe this interface is, I described this once. And let's say now I have like 4 different clusters. So for each of these clusters I had like, a list of other clusters from our previous tutorial. I just deleted them earlier today. So for now, I just have one tutorial instance, like one cluster here. So, and then I say what to do on that cluster. So the same bit of, I'm now like, in some sense, reverse engineering, like, what we do here in our job in this tutorial hands-on. So the same step. So the framework, I pre-configured the cluster to the framework and said it's a Slurm resource. So it knows like, it knows how to generate these macros. But like, now I need to tell, okay, for my application, this is very application specific. So these are resource specific, so just Slurm specific. And now I'll tell it for my application, I'll add these 3 modules and then finally run it using the application. And then the application, based on the user's input, it will put the right flags there. So I go here and I add those modules, module purge, the module load, the GNOS 9 and Singularity, and then like give my executable path as like in this case, as I was doing my own hands-on walking through in the earlier sessions, I just picked that from one of my training, the training account I was using, and then just put a pre-generated Singularity image of the GIF one we use there. So I configure all of this. I can give, let's say if I have multiple queues on the cluster, I can say what's my preferred or default one and some pre-configured inputs. So once I finish all of this, I'm kind of set. So, and you'll see also one of the reasons, like, where you'll see an NWS plot grayed out. Part of the reason is I did not deploy that. So part why you're seeing it's grayed out is it says, okay, I described all the inputs and outputs, what kind of images I want, but I kind of disable the resource for this tutorial. So you should probably see, this is the view you should see. If you'll go back, you'll see that you can use this the Mandelbrot application, but you don't have any resources for the Python plotting images, WARF output Python plot images. So you click that, the very first one. So I should be able to walk through with this step here. So and then you will see that the default values I mentioned, I configured as an administrator, show up here. You are welcome to change them. So the big thing, is we can what we have done is 2 things. One is made a simpler interface to the batch command. So the one advantage is now you can now have this gateway to be used by users who not necessarily have to learn how a Slurm submission works and how to configure this. They're just staying focused on their goal here. In this case, application. What are the inputs it will require, and the resources. You can use the predefined sets, or you can change them up to the maximum. I haven't configured because the cluster allowed did not have that setting. I didn't allow. But if your cluster has a maximum limits on how many nodes or cores you want the users to set, you can configure them. And then finally, you can save and launch. And now the gateway infrastructure will monitor the progress there. So while it's working it through, I can take questions. Any questions on, because we're skipping over, so I'll be happy to go into details on some of the mechanics of the framework we're using, or any questions. Otherwise, I'll just we'll just walk for those jobs to be completed on the cluster.
So I'm new to Science Gateways. I didn't know about this at all, and it seems like a very neat way of making these infrastructures more accessible to domain scientists and so on. In this case, this is not really container aware, right? It's just running the Singularity command, but it could be running any other command. So I guess there could be an even tighter integration with containers in the sense that, for example, it could ensure that you are running a specific hash version of an image or so on. Because right now, it's running the image that you built in your home directory. And that could conceivably change over time, right? So which would then hurt reproducibility, I guess, of this experiment.
Yes. So I think I'll take that into two questions first. Thanks, Eric, for pointing me about something I did not configure it right. So first, I would say that in the process, I'm sharing my screen to show some of these are very configurable. So I see that Eric pointed out these jobs I ran just now might be failing because I was using a wrong scratch location. Now I change it. So if you submitted a job before, please resubmit. I'll just submit this and I'll come back to answering that question. So I'll do is I'll go back to my job and I clone it so that I don't have to configure again my inputs and so on. So it will get me back all the inputs I gave before and I launch it. Yeah. Okay. Yeah. Sorry. I'll answer this. Try and answer this question now. So. So let's start with the reproducibility question. So I've used the home directory one. Yeah, with that I was first I wanted it to be running quickly, and we didn't want to add extra variables, but we should have probably a recorded versions of some tutorials. We use Singularity Hub, and I'll let Eric describe some history about Singularity Hub here. But we can take at least from a conceptual standpoint Docker Hub as an example. So the basic idea is an application, someone who is expert with the application, configures them and pushes them to a repository like Docker Hub, or use GitHub as that repository where you are managing those. And as you can, once you have it in the Docker or let's say GitHub, now you have a tag or a commit version, and then you can have others use it, and even further new versions, you'll get a new tag ID so that you are really they're immutable in some sense. So you can refer it back over and over again from different parts, and so in that sense, you're not quite addressing the reproducibility. At least you have a traceability back on which version you use, what was in there, so that when you bundle back your results you generated with this particular execution, you can look at that aspects. That sorry. I want to make sure that if I'm answering your question, feel free to more on that.
Yeah, no, sure, makes sense. I guess it would be putting too much, giving too much detail to the application user, I guess, if they had to be concerned with image versions and so on. So it should really be something that the administrator takes care of.
Yeah, and you are right. We could have even tighter integration between the sort of container deployment and the gateway. That's something we're working on nailing down better, because in theory you could just say here's an image, and the gateway middleware takes care of making sure that that image file is available where you're going to be running jobs. But that's sort of there are multiple layers to that problem as well.
I can imagine, yes.
Yeah, sorry, Suresh, I threw you a bug that was happening at the same time as you were answering your question.
Yeah, thanks, Eric, for jumping in. Yeah, so I just wanted to launch something which will go through. Sorry, I probably changed something. I deleted some configurations. My apologies, so that no one will launch to the POC 21 tutorial. So during that, I probably there's some configurations here. Apologies for that. Yeah, but hopefully you got the point across, what we are trying to do here. Yeah. So, and as Eric said, there's a whole set of longer issues, we want to, or longer opportunities, I would say, on how we can use these containers and apply them into more and more gateways, So I think it's coming there right now, and we are kind of we can just brainstorm them here too. Thomas, looks like you have a question. So briefly, you unmuting.
Yeah, I have a question.
Yeah.
Can you hear me? Can you hear me? Yeah. My question is because you mentioned at the beginning that your data flow is mostly based on files. that right? For these workflows that are basically launched behind the gateway, the data flow within the workflow is based on files. Is that correct?
Based on file, you said, sorry.
Based on file. Yeah, because you mentioned input-output files.
Yeah. Okay.
But isn't there like a data message transfer services that you offer that are potentially not based on files?
So, yeah, that's a good question. It really depends. As I was trying to say, like for example, for the data parsing frameworks and so on, we use stream-based data inputs. So where we can send messages over Apache Kafka queue, and then React. But for the most of the clusters, part of the reason you're seeing this file-based IO is kind of the reason we work backwards on the way HPC clusters work. So we try to mimic as much as what the examples today, what you've seen as how a typical batch job works. You need to get all your data stage into the working directory, construct your batch job description, and then submit it. So that's the example I was focusing on today. But in kind of that changes as you see other use cases like the serverless use cases you were pointing out earlier. Yeah, for serverless, typically we use kind of serverless mode. I will not directly call it. Yeah, you were mentioning some Apache frameworks. So we used to use Apache Vimsy, but now we heavily rely on a framework called Apache Helix. It's a I'll not get into the details unless you have any questions there. But yeah, using the Helix-based workflow orchestrations, you can integrate that with a Kafka-based message queue by the state being managed in Consul or Zookeeper-like infrastructures there.
Okay. Thank you.
Yeah, thanks so much. Okay, with that, probably you can end a little bit. But again, if you have questions, I have some backup slides or some other gateway interfaces I can walk you through. But just wanted to get this context for this tutorial. That we started off with looking at the whole introduction to the containers from Docker to Singularity, and now how can we make those Singularity runs through the gateway. And apologize, I didn't. With my configurations change, I wanted to show you how you look at the outputs, but hopefully you got the idea. With that, that's it for me. Thank you, everyone. Yeah, back to you, Eric.
Thank you, Suresh. So this actually concludes our planned activities for the day. I can let everyone go now and either go back to dinner or the rest of their work days. Thank you so much for attending and listening to our tutorial. I hope it was valuable. Please feel free to reach out through email or ping us on GitHub. All of our links are available in the Google Drive or on our GitHub account, and the recording will be in Whova. So yeah, unless anyone has questions, we'll call it a day.